We can start the first day of our second quantum machine learning workshop. My name is Paweł Gora. I'm one of the organizers. I'm a representative of QPoland and Quantum AI Foundation. These are two formal organizers of this event. Just some basic informations at the beginning. There are 2 days of classes, so we are starting now today, and tomorrow there will be the second session. I'm the lead organizer, but I was also supported by Jacob, Sebastian, and Tomek. So Jacob is our instructor today, and he'll be instructor tomorrow as well. And we also have two mentors, Sebastian and Tomasz. They are also available on Discord. If you have any questions, feel free to ask on Discord, or you can also try to ask your questions here on the chat, and maybe we can try to answer if we if we have time. The graphics were prepared by Aga Wolska from QPoland, so I would also like to acknowledge her. And the workshop will be based on the materials uh, prepared by Jacob, available on his GitHub repository, and they are open source under the GPT free license. All the lectures will be conducted here on Zoom. Discord is our backup option. If something goes wrong, then we can try to use Discord, but by default, we'll use Zoom, and as you can see, we are also recording this workshop, so we hope that the video will be later available on our YouTube channel if everything is fine. All the communication with mentors and questions should be posted on Discord, and we'll try to answer there. As I've told you during the lectures, you can also try to ask your questions here on the chat or raise your hand, and we'll see what we can do. We'll also try to answer some questions here on the chat, especially if the questions are related to organization of the event. And one important announcement is that you can also receive a certificate after solving the final tests. We'll share the details later on Discord. Now a few words about QPoland and the Quantum AI Foundation, because we go move to the uh, more merit part conducted by Jacob. So QPoland is a quantum cousin, or so-called Q cousin of QWORD. QWORD is an international organization, so formally it's an association registered in Estonia. It's a global network of individuals, groups, and communities collaborating on education and implementation of quantum technologies and on research activities. So we work together globally, internationally, to prepare educational materials that are open and freely available um, for people. And based on the materials that we develop together, we organize workshops. So actually, in this case, the training materials that we use, as I said, uh, they were prepared by Jacob um, individually. So thank you, Jacob, for sharing your work with us, of course. Uh, if you are interested in other keyword activities, both educational and research activities, you can join the Keywords Discord or follow its social media. So in particular, uh, we have several types of uh, educational workshops, starting from introductory level to more advanced intermediate level workshops. So actually, this QML workshop is in my opinion a bit more advanced than um, so definitely more advanced than introductory level workshops of Keyword, and it's similar level or maybe more even more advanced than intermediate level workshops. So I hope that you already have some good background in quantum computing, but just in case, most of the events that we organize are also recorded, so you can also watch the recordings on our YouTube channel to learn some concepts that you might have missed earlier. Okay, and as I said, QPoland is one of the Q cousins of QWORD. I can say that actually it was one of the 5 founding members of QWORD, and until today it's one of its most active Q cousins as well. So We usually organize at least 2 or 3 workshops per year, and we also organize several other activities like meetups, contests, conferences, hackathons. We release a newsletter, QPoland newsletter, so you can also follow our profiles and join our Discord, uh, follow our YouTube channel to stay up to date, and subscribe to our newsletter, of course. So here are the links, and I will later share my slides on Discord, so you should be able to follow our activities. And finally, a few words about the second organizer, Fundacja Quantum AI, or Quantum AI Foundation in English. So it's a non-profit organization um, registered in Poland. Sorry, I need to mute one person. It's a non-profit organization registered in Poland, in Warsaw. Its goal is to support education, research, and collaboration in new technologies and science, in particular AI and quantum computing, and quantum AI, quantum machine learning as well, but also other fields of math, computer science, and physics. And Fundacja Quantum AI, or Quantum AI Foundation, is the formal legal organizer of most of the QPoland's events. Um, so it supports QPoland's activities formally. And here I would like to thank you for your attention. If you have any questions, you can try to contact me on Discord or send me an email. Um, and yeah, you can also try to post your questions here on the chat, and I will try to answer. Uh, there was a question about becoming Q cousin of Qword. So first of all, you have to check the list of the current list of Q cousins. It's available on the Qword's website, and I will later share a link here on the chat. And then on the website of the Q cousins department of Qword, you can also find the guidelines for Q cousins, and then you will see all the instructions to establish a new Q cousin in your country. So in particular, there are some requirements, like you need to have a team of at least 2 people. The more is better, of course. You need to have strong connections with academia, like at least one person should be a senior researcher affiliated at the university or a research institution at least, or a PhD student, PhD candidate at least, and you need to have a prior experience with some keywords events like this introductory level or intermediate level workshop. So you need to, or at least one of the members of your team um, have to has to pass successfully pass one of the previous keyword workshops. So these are the most important formal requirements to establish a new Q cousin group. I will later share the details here on the chat um, and on the Discord. Okay, let me check if there are some other questions. All right, I do not see more questions now, and I can see that we have more than 100 participants already, which is great. I hope that all of you will enjoy this workshop. I'm pretty sure that it will be successful. The first edition in April was very good. Thanks to Jacob as well, thanks to all our mentors. So, if there are no more questions, I think we can start the merit part.
Thank you, Pavel. Before I get into the main presentation, just to let you know that if in the future you get lost the links to slides and the links to GitHub, you could go to my website, jacobcybulski.com. You could go to presentations, and at the moment, this presentation is one of the 2 top presentations. And at the moment, you have a link to GitHub only, but you will have other links here as well. So slides are in slides directory on GitHub. I have notebooks and lots of explanation what's in here. The most important one is that there are some requirements for software, how to install. We have all the details on software installation on Discord. So if you're preparing to run some of those notebooks, make sure that you install software according to those specifications. There is a requirements.txt file. And if you know how to load it into Python, how to create the virtual environment, whether it's Anaconda or Python virtual environment, you'll be set. But I'd like to stress at the very beginning that if you install the most recent versions or the old versions, this may not work as you expected. But I think I updated all the versions recently, a few days ago. So it should be working on all up-to-date versions of Torch and Penny. Okay, so let me get into the presentation now. So I'll, okay. Okay, so I'm Jacob Cybulski of Unquanted. I'm based in Australia. Unquanted is a small startup which I'm managing, and we're very busy at the moment. Hopefully, in a few days' time, we'll have a working website. I'll work with my technical people to get it up and running. Okay, so this workshop is on quantum machine learning. It's an introduction, and this introduction, let me just put my video out so I reduce the traffic. So this introduction, it is assuming that you already have some knowledge of quantum computing, some knowledge of machine learning, and definitely some Python. Okay, so if you've done previously some course in data science, you're well set, or some analytics course, you're pretty much well prepared for this course. But quantum computing, the basic of knowledge of quantum computing is necessary. So we're going to cover a lot of different aspects here over 2 days. There'll be 4 sessions, and this preliminary sessions are going to introduce some basic concepts, and I will refer to your knowledge of fundamentals of quantum computing, and we're going to build up your knowledge to some relatively advanced aspects of quantum machine learning. So that's what is awaiting you. Our team, we have 4 key people that Pavel already mentioned those people. So we have Pavel Gora, who spoke a moment ago. We have Sebastian Zając, who's assistant professor at SGH Warsaw School of Economics. He's a mentor. Tomek Rybotycki, who's a QML researcher. And myself, Jacob Cybulski, and most of my time is spent on quantum computing and quantum machine learning in particular. So we're here to assist you, and we will assist you during the session, and after the sessions and between the sessions as well on Discord. So what is exactly quantum machine learning? And there's not a simple answer to that, and people have a variety of different ideas. The way I see it, it's an intersection of 3 disciplines, which is quantum mechanics, computer science, mathematics, and statistics, and maybe more specifically is quantum computing, machine learning, and part of mathematics, which is the foundation of quantum mechanics. And so there's many applications of quantum machine learning, which touch upon the economy, environment, people, organizations, and society. And some of those applications are very successful and some less successful. The most successful ones are in chemistry and pharmaceutical industry, perhaps because quantum computing and the phenomena involved in quantum computing are so close to the phenomena in the processes described by this discipline. And this is a lot of related areas like materials, manufacturing, energy resources. And this is probably the mainstream of the greatest success of quantum machine learning and quantum computing in particular. Then we have finance and insurance, which is rising up, perhaps because mathematics is in many aspects similar. And then we have other areas in networking security, huge area, great successes, which attracts a lot of funds from governments and defense. But we have business, transport, logistics, aerospace, automotive industry, and definitely medical, healthcare, biotechnology, and many, many more. So we have applications. There's a lot of articles and papers which you could access to explore those areas further. If I could ask you not to write on the screen, because if you touch the screen, everybody will have smudges on it. Okay, so um, especially don't leave your child in front of the computer with the mouse in the hand, because we had that in the past. Okay, so we have two objectives here because we have people that come maybe from physics and maybe they are very well versed in quantum mechanics. And perhaps this workshop will be to build their knowledge in machine learning. And if you are already a computer scientist, maybe, so you have a good grounding in machine learning. So you're going to learn more about the quantum. So we have the Q people and ML people, and they will learn something that other people may know already. So I hope that this will not bore one or the other group of people. I'm going to introduce some basics of machine learning and some basics of quantum machine learning. And together, we're going to figure out how the two work together. So what you see here, it's a quantum circuit, and this is something that you should be very familiar with because you've done already some quantum computing beforehand. Um, Quantum machine learning is about creating models, which are quantum models, and training them, evolving them to um, predict some aspects, some phenomena, or to describe them, or to explain what happened perhaps in the past in a formal way. And to do that, we need to have ability to create the quantum models and then alter them, optimize them to fit the data. Like in machine learning, the data is usually coming from it's a sample of data available somewhere out there. And based on the available data, you try to create a model which not only could work with the data available to you, but could also apply to new data that will come in the future. And so it's a typical scenario um, uh, for machine learning. So one issue with the quantum circuit that you're familiar with is that once you create the circuit, everything's fixed in it. And the circuit is static. It consists of qubits, gates. We have entanglements, measurements, and every gate is well described with a specific values. It's ready to be compiled and submitted to quantum machine or the simulator for execution. So there's nothing here that can be trained, nothing here that could be optimized. So there must be some other tool, technique that will allow to loosen up this rigidity of the quantum circuit and create some placeholders for certain parameters which could be optimized. And so there is such a technique, and we create templates. We often call them ansatz or parameterized quantum circuits. And those parameters are available, they become variable, and they could be manipulated by the classical optimizer. So that's great. So we have this ability and the ability to vary parts of the circuit and train the parameters is something that we will rely on. The other part is that we need to be able to bring some input into this circuit. And of course, the input is not coming from qubits, initialization of qubits from input like we are used to in classical programs, we need to encode data into the circuit. And encoding techniques are quite complex, and there's a variety of different strategies that you could employ for doing so. We'll talk about it in a second. And finally, we have the block at the end, where you measure, you specify your observables, and they get turned into measurements, very specific and sometimes very complex measurements. Eventually, you get classical data out, and that classical data, the result of the execution of the circuit, could be, it is presented in a classical data and could be compared against what you expect. Okay, so we have the structure and the facility to support the optimization techniques which are available in machine learning. Okay, let's start with data encoding or embedding. And there are many, many methods of data embedding in quantum circuits. We have basis encoding, angle encoding, amplitude encoding, QRAM encoding, and many, many others. And there's a great book here at the bottom, written by Maria Schult and Francesco Petruccioni, Machine Learning with Quantum Computers, second edition, spring of 2021. And it describes a variety of aspects related to quantum machine learning in particular, but very specifically also data encoding strategies. So you could get more insights from this book. I'm going to focus on the simplest of the approaches, the angle encoding. And the reason for that is that it facilitates encoding not only binary values, not only integers, but also floating point numbers. And the representation of those numbers in qubits is very simple because we rotate the quantum state of the qubit in X, Y, or Z coordinates. So here we have two strategies. The rotation occurs around the Y-axis, so we use the RY gate. And we need to have some reference point from which the rotation starts. And perhaps it's the ZZ axis, and we rotate to the right, and we could accommodate up to 2 pi possible values. We'll come back to that because maybe 2 pi is too much. Another possibility, if you want to represent negative and positive values, you could start with the cat state, which is achieved with Hadamard gate. And then you can rotate up towards Z-axis or down. And you could represent negative and positive values. And there's many, many others. Basically, you need to decide how you're going to interpret your values while you encode them, and then back as you get those values from the measurements. So need to be careful. And here's just an example. If we create 3 qubits and we put 3 different rotations, and those rotations will be, to be specific, I encode arc cosine of specific values. On measurement, I should get the amplitude, which is back the same values. So those are the angles that we're going to apply. Now we measure those values. Now the problem is, how do we measure it? So we could measure them as probabilities. We could measure them as amplitude, as expected values. So we have different outcomes. If you measure them as probabilities, you should expect to get some probability distributions between what you get 0 and 1 as an outcome on each qubit. As you can see here, we have different probabilities. We have pairs of numbers on measurement, or if you use expectation values, you will get some positive, some negative values between -1 and 1. And I assume that you're familiar with those concepts. You understand the probabilistic distribution of measurement outcomes, and you know what expectation values are. Okay, so just keep it in mind that if you refer to expectation values, the possible outcome is -1 and 1, and then you could get some aggregate accumulation of statistical um, mean of what is expected to appear on the measurement. Okay, so keep it in mind that we're going to refer to those things. There's other encoding techniques. For example, amplitude encoding is fantastic because the way you encode your numbers on input is exactly what you're going to get as a probability distribution on output. And so you have great consistency between encoded values and values on output. The only problem with that approach is that amplitude encoding is such that every collection of numbers you are encoding, it actually changes the structure of the circuit. So sometimes the circuits are longer, sometimes they're shorter, sometimes wider. And so if you want to run such an application based on this on a quantum processing unit or on some accelerator on the GPU, then it becomes very inefficient. And some programming languages like Penny or Qiskit, they actually don't allow amplitude encoding to be run on accelerated devices. So that's a bit of a problem, and but there's many others. So definitely, please explore other possibilities. We're going to take the simple one, the amplitude encoding, and I'll try to make it very consistent throughout this workshop. Just one more thing is that if you go back to this slide, here we have encoding block of input values. One rotation, in this case, is using a rotation around x-axis. And it's at the very beginning of the circuit. So that's fine. In a lot of quantum neural network structures, that's more or less what happens. We have the encoding block, then we have the answers, then we have measuring block in this order. But this doesn't have to be that way. And soon I'll be showing you structures where, for example, input is encoded several times every layer of the circuit. And this is called data re-uploading. And this is one of the most successful ways of getting good sort of well-performing quantum model, which works very well. So it's sort of like reminding the circuit, this is the data you're working on, and so you could accumulate the effect of doing so across the flow of state changes throughout the circuit. Now, the angle encoding. The angle encoding is simple, but just keep it in mind that we have a limited range of values available for encoding. Basically, it's values from 0 to 2 pi or from minus pi to pi. So it's like 2 pi possibilities. If you try to encode more than what's available, then we start getting problems. In fact, we start getting problems early on because if we measure the encoded value, which is one of the vectors shown, let's say in blue, after the 2 pi, if we measure the result, from the measurement point of view, it doesn't really matter on which side of the block sphere is your vector, whether it's on the right-hand side or the left-hand side. It will give exactly the same value on measurement. So there is a conflict already in what the measurement is giving you, the amplitude, versus what was the value encoded on the block sphere. So that is the problem. However, we know that during the manipulation of the state of the qubit, especially if the manipulations around x, y, and z coordinates, your state is going to end up anywhere on the block sphere. Okay, but what's important is how you encode it to start with. What is worse, actually, if you start encoding from 0 to pi, then from pi to 2 pi, and go further. So in this case, this is the orange colors, we instantly get into conflict between encoded values. So in this case, it's a conflict from the very beginning. You create a dirty encoding values. And this will have a tremendous effect on any optimization later on. Okay, so keep it in mind, this is an issue. We need to keep your encoding of data clean at the very beginning. If you started with a problem, it doesn't matter what you do later on. It's going to come back and hit you right in the face. So one principle is distinct data values should be mapping onto distinct amplitude of measurements, or angles at least. The second problem is that some applications could map the same data values into different amplitudes. So on some occasions, the same value is going to end up in a specific position on the block sphere, and then another y could be another position. For example, if you take a sine function, and we know the sine is going to repeat itself from 0 to pi and 2 pi, and after 2 pi, this is exactly the same values. But if after 2 pi, suddenly you're mapping it into different positions, not exactly the same that you planned at the very beginning, that will lead to conflict. So we have multiple values hitting the same representation. So two principles to keep in mind. Distinct values should map onto distinct angles and amplitudes, and the same data values should always map into identical amplitudes and angles. Okay, so keep it very consistent. Now, the ansatz is transforming the state of the circuit layer by layer, and eventually gets the final state of the circuit, which needs to be measured. And that measurement is, of course, every qubit measured is going to give you either 0 or 1 outcome if it's probability measurement, or -1 to 1 if this is the expectation value measurement. And the nice thing is that in Pendelane, as opposed to Qiskit, you have support for those two distinct interpretations of collapse of the qubit state. If you do in Qiskit, to get expectation values, you need to actually write a little program to retrieve that value and interpret it that way. Okay, so we get binary result. And of course, we would like to be able to measure things much more complicated. We want to be able to measure integers. We want to measure floating point numbers. We want to measure multiple values on output. How can we do that? Okay, let's start with the first simple fact. We could measure either all qubits, or we could measure one or very few qubits. We could also measure qubits in groups. Okay, so actually the third approach is becoming not an option, especially that we have now large quantum machines which could support thousands of qubits, and there is no way you could actually measure 1,000 qubits and make any sense of it. There is no way to represent the result 2 to the power of 1,000. It's ridiculous. So definitely we need to be able to keep it in mind that something that's called global cost measurement, measuring all qubits, it is only has limited applications to very small circuits. So we need to be able to be selective and measure only some qubits or 1 qubit. Okay, so that's a local cost measurement. I'll explain that later on again. So that's the starting point. Okay, so if we measure 1 qubit, if we measure the 1 qubit, let's say we have the outcome 0, 1. So what does it mean? It's not much. You need to actually get repeated measurement, and you create number of shots at measurement, and then repeated measurement give you distribution of outcomes, which depends on the state of that qubit. We have a lot of questions here, but Tomek is answering them, so it's great. So really, don't expect me to answer straight away. I will be looking at the questions later on as well. Okay. So we have a distribution of results for how many times the 0 appeared and how many times 1 appeared on your measurements. And of course, we need to look at the distribution of that single outcome. And from that, we could say, okay, if it's the bar is high on 0, that is the binary outcome 0. If the bar is higher on 1, that's the outcome. So that makes sense. However, you could also look at it differently. You could monitor the bar of 0 associated with 0 outcome, and you could treat it as a floating point number between 0 and 1. And you could actually train the model on that outcome, on that frequency of outcomes in this range, 0 to 1. So suddenly we have a floating point number as an outcome on measurement. So it's nothing to do with measurement, it's to do with interpretation after the measurements were taken. The second possibility, let's say we're going to measure all qubits, and we have a combination of different outcomes of qubit values, 0, 0, 0, 0, 0, 1, and so on, up to 1, 1, 1, 1, 1, 1. And if we repeat the measurement many times, then we have this probability distribution or this distribution of expected values for every single combination of qubit outcomes. And again, we could look at the height of the bar and say the most probably outcome gives you the expected result as a floating point number, and vice versa. You could say the actual combination of outcomes on qubits measurements, 0, 1, 1, 1, this is the integer I want to consider as my result. And suddenly we could get integer representation as your outcome. And then you could look at the whole distribution of outcomes, and you could actually train the model to give a specific distribution shape. And that shape gives you multiple values. And also this shape is going to give you a probability distribution as if that's what you want to get as a result. So we have a lot of possibilities, and everything boils down to the simplest measurement, which is either probability measurement on a single qubit or its expectation value on a single qubit. It could be across all qubits, monitoring single outcomes on qubits, or look at them as a whole distribution. And again, it's a reference to Maria Schulte and Francesca Petrucciani. There's more information you could get there. So the good thing is that we could interpret the measurement outcomes in many different ways. Now, beware. The more measurements you're going to include, the more complexity is going to be required for interpretations. What does it mean? If you add one extra measurement, it multiplies by 2 the number of combination of qubit outcomes. Okay, so suddenly we have double the number of outcomes. And it means also that suddenly, if you keep the same number of measurements conducted, number of shots, all those bars are going to be reduced height by half. If you add another qubit, they reduce the height by 1/4. If you add a lot of qubits extra at the measure, suddenly you're going to have very small bars at the bottom. They'll be just near 0, all of them. So to be able to get a realistic result in probabilistic distribution, you need to, with every added qubit, you need to really multiply the number of measurement outcomes by 2. So your number of experiments, the number of shots will have to grow exponentially with the number of added qubits. So this is the problem, which is not only the problem with what happens in quantum space, is the practical problem. Do you have enough time to wait to get you a realistic and precise measurement of your circuit state? Okay, so let's look at what happens in the middle, is the ansatz design. We have here the same structure we saw before. When you design this, of course, you could rely on standard templates which come from Penny or Qiskit. And those templates are going to give you some configuration of gates for encoding data, some configuration of gates for to keep the parameters and parameter blocks, and then some configuration of entanglements. Okay, so there's standard ready-made solutions for you, but you need to somehow parameterize this. You need to say, well, what's the width of the circuit? How many qubits we want? It may depend on how much data you've got in input. It may depend on how many parameters you need, regardless of the size of the input. Okay, so you need to keep planning that. What is the depth? How many layers? How deep is this circuit? The deeper it is, the more parameters you're going to add and the more entanglements. Is this good? Oh, it depends. I'll talk about it in a second. It actually rises the complexity. With every parameter added, we multiply, we double, we add another dimension to the parameter space for the optimizer. How many dimensions? The number of parameters. What is the structure? Should it be a flat structure like here, every layer is the same, or should be funneling first out and then back in, like in a classical neural network? And so we will rely on simple structures, but you can build your own custom structure, and we'll show you that almost immediately today. Okay, so the ansatz layer consists of rotation blocks. So it could be a single rotation around X, Y, or Z, or three rotations. And in three pairs, you get extra parameters. And the CNOT gates, which is the entangling gates. Now, the other side, we have the classical optimization. The optimization of quantum circuits. It's really a hybrid approach. When you execute the circuit, we could rely on a quantum machine or the simulator. When the training happens, you rely on the classical optimization technique. There are some pure quantum techniques for quantum machine learning, and we're going to stick to something simple. It's an introduction only. Okay, so we need to be able to select, first of all, the platform on which we're going to train that model. Is it going to be on a simulator, the CPU, your laptop, or your home machine? Is it going to be accelerators, GPUs or TPUs, which you may have on a gaming machine, or you may be sitting on a data center with a lot of NVIDIA powerful GPUs? Or do you have access to real quantum machine? And so the device, which is your target device, is very important. It may actually have a huge impact on the way you're going to design that. The second one is that you have a choice of different optimizers. Some of them are gradient-based, such as Adam, Nesterov Adam, SPSA. Some could be linear approximation methods, very popular in Qiskit, Kobela. Nonlinear approximation method like BFGS, or the optimizers which actually understand what happens in the quantum space, the quantum natural gradient optimizers. The other aspect is how we're going to measure the difference between expected outcome and the result of your quantum calculation. Is it going to be mean absolute error, mean square error, R squared, Huber, Poisson, cross entropy, hinge embedding, Kullback-Leibniz divergence, depending on is it a classification task, is it an estimation task, or is it a task which compares probability distributions? Okay, so you need to think about that. Okay, so there's a lot of choices, and Pendulane delivers those choices, and so is Qiskit. They have differences, and mainly because Pendulane is really designed for quantum machine learning in particular, and Pendulane it's really leaning towards differential programming techniques. So everything in Pendulane is a function, and that function must be differentiable, and every weight in this circuit will have a gradient, and you can manipulate those gradients. So this is the complexity of Pendulane, but it's also easier to meet the requirements of classical machine learning. So beware adding qubits as parameters and entanglements. So the number of states represented by circuit grows exponentially with the number of qubits. Of course, the presence of entanglement gives you much smaller dimensionality because suddenly the qubits get correlated. But this correlation still lives in highly dimensional space. Okay, so this will be very important to understand that. Okay, so we start with classical deep learning models and how we go about optimization. So in deep learning model, such as neural network, the network represents some problem, and we hope that we can train it to represent that problem in weights and biases attached to the links between the nodes, between the neurons. So each node has some activation function, which is calculated as a weighted sum of nodes. It's some bias, which is added, and activation function produces some nonlinear transformation of that aggregation of weights of connected neurons from the previous layer. Okay, so all possible model parameterizations. So if you look at all possible parameters, each different parameter set is attached to a specific instance of your model. So that those represent models. The models which the performance is assessed in terms of some cost. So you specify the loss function, which gives you the amount of error generated on the run of this particular model. And when you compare it to expected value, you get the loss. Now, if you do it across all possible data available to your training set, you accumulate them in some way, and that gives you the cost of running that of that particular run. And the cost really gives you the aggregate value of the error. And you think if you're going to get really bad result, you take your wallet out and you pay for that. You get penalized. It's a cost. Okay, so what's going to happen during the optimization? The optimizer starts from some point, and then it runs the model, it calculates the cost, and calculates the gradient. It calculates the gradient. It actually shows it figures out which way is the way down towards the optimum. It assumes there is some kind of a valley and more or less smooth way on the way down. So the gradients give you the inclination down towards the bottom of that valley. So at each step, the optimizer is trying to find the cost. It calculates the gradient, and it's leading you down. It may use some other information, such the momentum of moving it down, the second differentiation of that aspect. Okay, so it's moving lower and lower, and eventually, hopefully, it arrives at the minimum. It could be it's a local minimum, so it may be it's a lot of bumps on the way to the global minimum, and maybe needs some statistical aspect to shake it out, shake the optimizer out of the a small pothole, and then it could perhaps find the way down. So that's what happens in a deep learning model. So the gradient optimizers are going to rely on the gradients, and you have stochastic optimizers that could assist with some stochastic event with the gradients and avoiding the minimum, or you could use the momentum to use the momentum of this to get you out of the local pothole. Okay, you could also use backpropagation, and backpropagation it's understanding how the calculation of all the gradients propagates through the from the network. Okay, so our backpropagation assists in calculating what happens in every single node of the neural network. Okay, so that's what happens in the classical case. What happens in a quantum model? This is becoming much more complicated. So the complication is that if we have a circuit and you run it, the circuit actually, as it executes, that transforms the state of the initial state of the circuit, and then layer by layer, the state gets transformed until it finds the final state. And now all those transformations of states, it happens in a quantum state space, the Hilbert space. So we start from the initial state, and then we go from layer to layer. The state gets transformed until the result is coming. This is not actually the solution yet to the optimization is just one run of the circuit. And during this run, the states of the circuit are changing around the Hilbert space. Okay, that's fine. So uh, we put another data item on input. We encode it differently, we run it, and we have a different path taken. Then we put another data item. We have a different path taken. Then let's say we're going to change the parameters of the optimizer is going to improve and change the parameters, and we have different set of paths. So there's a lot of complexity happening there, which is not really visible to the optimizer. It's all happening in the Hilbert space. Okay, what optimizer can see, the classical optimizers, is only the parameters which are attached to gates sitting on qubits. The classical optimizer is blind, completely blind to what's happening underneath in the quantum space. And that's actually is a very important thing to remember. For example, the optimizer does not know that if you change the parameter in a gate on the qubit, the third qubit, because the qubits are entangled, it actually changes parameters far away from that parameter in the circuit. It actually changes the parameters of the model that optimizer is trying to improve. So this is what's called the non-local interactions between the parameters, and there are non-local interactions between gradients. So if you change the parameter value, the weight, you're also changing the gradient, which is attached to this weight. So that is very difficult for classical optimizers to figure out. They don't figure it out. They simply know there is a problem with the optimization. It's much harder than it is with the classical models where those interactions don't happen. Okay, so we try to have very small learning steps, and eventually the optimizer can get it and improve it. But there is definitely this relationship between what happens in the Hilbert space, which perhaps is given there's some kind of Hamiltonian describing the process or the state of the process, and what happens with the parameter space, which is visible to the classical optimization. Okay, so keep it in mind, we have this duality of representations. One representation is a quantum representation, which relies on qubits, their correlations or the entanglement, the parameters which are sitting on gates. Those gates are performing rotations of qubit states. None of that is visible to the optimizer. As a question, evolution of the state is linear, but data is encoded in non-linear way. The data is encoded in a linear way. Okay, so basically, the only nonlinear operation in a circuit is a measurement. The circuit is a unitary circuit, so every standard operation is unitary, and so the transformations of the state are completely linear, unless you put a measurement in the middle, or you reinitialize the circuit, or you use some kind of a matrix operations, which is giving you a non-unitary transformation. Okay, so what else is happening there in the parameter space when we have entangled qubit gradients? Okay, so the more entanglements you have, the more non-local interactions, the harder the job for the optimizer. The second thing is happening, if you have a lot of entanglements, that actually creates correlations between the parameters. And so if you look at multidimensional space, if some of the parameters get correlated, you eliminate some of the dimensions, not necessarily in a, it may not be aligned with the coordinate system, but you basically squeeze and squash your representation. So in such a case, if the optimizer would expect to have a nice valley of costs, that valley gets squashed and is narrow in the parameter space. And that is causing another problem for the optimizer, because the optimization process uh, is looking at a very deformed space of parameters, which is unexpected, but the optimizer doesn't really know about what's happening there. Um, there's another issue is that you can't use the optimization techniques which rely on gradient descent, especially if you look at the quantum machine execution, because you cannot look at any intermediate, you cannot actually look into what happens in qubit as the qubit states are changing and the parameters are changing. So, but what we can do is to look at the global gradients, the global um, space where every node is a model, not necessarily is a particular parameter. Okay, so we have other optimization techniques such as stochastic optimization techniques, which are very effective, but only when the cost landscape is very smooth. Other techniques such as particle swarm optimizers, but there's a lot of calculations. They are good for smaller models. So we have here enough complexity from your Hilbert space, and that we don't need to have very complex optimization techniques. But people are exploring different options. What we really want is to have the optimization technique, which is solely based in the quantum representation rather than classical representation. So at the moment, all we know is how to transport well-known techniques and approaches, which are borrowed from machine learning, and we try to apply them in quantum machine learning. Okay, so that's what we teach you in this introductory course, but there are new research approaches to how to actually optimize the quantum model in a quantum space itself, rather than relying on classic computation to assist it. So we're getting to a demo, and we're going to use Pendelane. So what's so special about Pendelane as opposed to say Qiskit? The first thing is everything in Pendelane is a function. So that's the first thing. It's a circuit is a function. The optimizer is a function. So everything is smooth and transforms easily one into another. It's a function of it, the function of the function. That goes well with quantum mechanics, where every operation is relying on another operation's result. Okay, so it's close to quantum mechanics. It supports differentiable programming paradigm. That means the circuit is a differentiable function. A matrix is a differentiable operation. The Python function is a differentiable function. So the great thing about it is that you could link them together, and you could apply and combine functions in many different ways, so that one component is a quantum component, another component is a mathematical object like a matrix, another component is a bit of Python code, and you could link them. So you have hybrid solutions. And one of my session 0 examples is showing you how to do it in Pendelane. Second, it integrates seamlessly with Python, and it's available from other programming languages, usually as a wrapper around Python. It has a range of operations for state preparation, gates, measurement, like any other platform. It has many standard algorithms available to you. It executes on simulators and quantum hardware, on accelerators. It supports error mitigation, maybe not to the extent that you can find it in Qiskit. So Qiskit got a fantastic library of error mitigation techniques. Qiskit, the core of the Qiskit at the moment, although Qiskit is also platform independent, but the core of it is depending on IBM machines. The core of Pendelane, it's relating to Xanadu quantum machines, which are photonic machines, and they are very different type of hardware in both. So usually the quantum machine underneath drives that development. Okay, so It has a lot of support for gradient manipulation. If you used Qiskit before, you may not even have seen gradients. You may have been constructing um, circuits, manipulating circuits, running the circuits, optimizing the circuits, and the word gradient never occurred. Here, the gradient is one of the first things that appears, and Pendulane provides its own library of gradient manipulation, but also allows you to link in with gradient management of other platforms like JAX, PyTorch, Keras, TensorFlow, and NumPy. I mentioned suppose hybrid quantum classical models. It's very easy to combine them together. Um, and it also has ability to support hardware compatible gradients. So if you use uh, TensorFlow or PyTorch, and PyTorch specifically, let's say we have NVIDIA GPU that PyTorch is running on. And so the gradients will be hardware specific for your accelerator. It provides lots of quantum models. Probably the number of models supported is more limited than Qiskit. So we have quantum neural networks, quantum kernels, Fourier models, and you have a lot of non-standard models in Qiskit. Here they say, yep, if you want more, implement your own or get the library from someone else. Can be extended with models and optimization techniques from other software development kits like PyTorch and TensorFlow. So basically, all the specific models could come from other libraries. Okay, so we're going to, again, I'm going to walk you through some examples and create some very simple models. And we're going to learn how to initialize the model weight, what the model looks like, and hopefully to learn how to optimize those models, how to persist and have sleepless nights and headache. Okay, so it's awaiting you next. So what I'm going to do, oh, one more thing. It's recommended readings. I mentioned this book, Maria Schult, Francesco Petruccioni. It's not cheap, but it's a great book to have. The two books from Tackett. This is the publisher which publishes very cheap books and a lot of programming books. So this book is a lot of mathematics and gives you good foundation for quantum machine learning. And it's the type of book people write that will not get obsolete very quickly. If you have a book with Python code and Qiskit or Pendulane, especially Qiskit, the book is obsolete by the time it's published because Qiskit is changing so rapidly. Okay, so that's this book by Elias Combaro, Samuel Gonzalez Castillo, Practical Guide to Quantum Machine Learning and Quantum Optimization. Is a great book for those who like to dirty their hands with code. And it's got examples of code in Qiskit and Pendulane and something else. Okay, so it's a programming approach. It gives you also some fundamentals of mathematical fundamentals of quantum machine learning. I recommend this book, Dancing with Qubits. It's a second edition by Robert Suter. And it's a great book introducing you to the mathematics of quantum computing. So it's nothing to do with quantum machine learning. It's all to do with understanding the maths behind quantum computing. There's some other good books on mathematics for quantum computing. I like this one. A couple of papers that you may want to get. There's a paper from 2020, Pendulane, Automatic Differentiation of Hybrid Quantum Classical Computation. It walks you through what Pendulane can do and what are the facilities. And another great book, a great paper. It's a very big paper by Anna David and many others, which give you a review of different modern applications of machine learning in quantum sciences. So they walk you through different models and the mathematical formulations and the circuits and others. So it's a great review of what is happening in the field. Okay, so let's get you to example. You will find my website, jacobcybulski.com. If you go to presentations, and this at the moment, this is one of the top two presentations. You will have later on links to to slides, but if you go to GitHub directly, you could find my slides for all 4 sessions in here, PDFs. And of course, you got the code. Okay, so the notebooks and description of everything. So if you know how to use Git, you could clone this repository and then keep it up to date, as I hope I'm not going to change anything unless some disaster happens. Um, but just a bit of explanation. Those notebooks are the notebooks related to the tasks we're going to use. So we have here exploratory notebooks, S00. I mentioned, for example, exploring the hybrid models, where you could build a hybrid model consisting of functions and circuits and matrices. And I'm going to start with exploring the tiny model, which you were supposed to look at it yourself, but I'll walk you through this. And some of those notebooks, they're going to refer to my utility functions. And those utility functions are currently in the same directory. On my machine, I have it in a different directory, and that could explain some unusual things, which I'll show you in a second. Okay, so let's get into the example. I'm going to start with exploring tiny model. So this is the explore tiny model. I did put it here on the right-hand side, the tasks for the next notebook. So I'm going to keep it here. We can ignore it for a second, but it will be important to see what we're going to do next. Okay, so first, because on my machine, I keep the utilities in a different folder than the current folder. I add the extra search, and let me just restart the kernel. I clear all the outputs as well. So I'll do it again. And I'm getting some standard functions, standard libraries. I assume you're very comfortable with Python. Now, I import the utilities. In your case, utilities are in the same folder as the main the notebooks. In my case, it's going to parent directory and down. I will import Penelane and Torch. Okay, first thing you notice here, that makes sense. Penelane wants to call itself quantum machine learning, so QML. And the next statement says, import NumPy from Penelane as NP. So Penelane has rewritten NumPy. It keeps it always up to date. Basically, in every array in this version of Penelane, of NumPy, is a tensor. Okay, so hopefully you're familiar with what the tensors are. I will assume that you know this. Okay, so that's very important. Don't import normal NumPy. Use the NumPy from Penelane. Okay. The next thing we need to decide, what is the device that I'm going to run it on? The device name is actually given in terms of a qubit. So we have different qubits. The default qubit, it's a state vector simulation. It's running on a CPU. We could have a lightning qubit. It's a high performance qubit written in C++, and you need to actually attach the lightning library of Penelane. You could attach the library for running on a GPU. It's a GPU simulation for NVIDIA cards. You could actually run it as tensor networks, or run it on a Qiskit machine, a remote machine, or use some other state simulations. So there's about 40 different devices that Penelane can run for. The trick is to really understand that some of those devices have constraints. So some of the options will not work on one type of qubit, but will work on another type of qubit, will work on the quantum machine, but not on on some specific accelerator. So you need to be able to be careful what you choose. We're going to use default qubit. It's a standard qubit running on CPU. So the first thing is I'm going to create some data. So you can see I'm using NumPy array. And here is interesting thing is since this is no longer NumPy, I can request gradients to be attached to those values. So the weights will be the ones that the optimizer will be manipulating. They always require gradients. The plain data does not require gradients. So what do they look like? So instantly you can see it's a tensor. So it's not no longer array, it's a tensor. And you can see that the weights are values, but they require gradients. Okay. Next thing is that I'm going to define a circuit. So if you're familiar with any other platform like Qiskit, that's very familiar. So we specify a device. So that was the device name they used, which was the default qubit. I specify the actual hardware device that we're going to link in, and instantly I specify how many qubits I will be using. Okay, and sometimes you create a circuit of 5 qubits, but due to penny lane optimization, it may require 2 extra qubits. So we specify how many qubits overall it will require. Penny lane calls them wires. Okay, shots, how many times I'm going to execute my circuit during the execution. So it's a device specification. And then I create the circuit. The circuit is a function. And you can see a decorator here, which says this circuit, when it's executing, it will create a quantum node. Okay, so quantum node is actually the circuit. I just called it a circuit because I know that that's what I want. But this is just a plain function, which I'll show you in the next session how you could actually change the way you deal with circuits. But this is the simplest way. We put a decorator, and the decorator specifies this is a quantum node, it's a circuit, which will be running on this device. And what the function does, we specify the inputs, we specify the outputs, and then we build the circuit. So what happens from the moment we execute it, at the very beginning, the quantum node is created. And then as side effect, we could be by calling variety of different APIs, the functions from penny lane libraries, we are going to either attach the gates, like the rotation gates, on specific wires or qubits and rotated by the value specified in the 0th item of the input. And then the next one. So we use the data flowing in through the parameters. As a side effect, the circuit was created, and then we specify at the end what type of measurement I want to return. So it's a probability distribution by measuring 2 qubits at the end. The number of wires, the wire will be 0 and a 1. Okay, so we just create a circuit. And unlike what you do in other platforms, we can draw it and we could run it exactly like we call a function. So first of all, drawing it. That draw circuit is coming from my library, utility function. I'll show you later on how to do it ugly way in the penny lane. This is the relying on matplotlib beautiful drawing. Okay, so this is what it looks like. If we can look at details here, the first thing you can see is we do not draw the circuit with empty parameter values. We draw the circuit when it's running. So what happens is that the circuits don't exist in absence. The circuits are created as a side effect of running the function. So because the function is running, it's instantiating parameters from its inputs and the weights. Only then the circuit is created and available for drawing. So there's no such thing as a static, unparameterized or empty circuit. Okay, so that's the first thing. There's no circuit in isolation. The circuit exists only when it's running. That actually comes from the whole idea of photonic machines. When photonic machines are creating circuits, they create the circuits just at the time where the laser beams are creating and stitching up the gates. It's happening at that point. It's creating the circuit, instantiating and flowing them all in space. They exist in vacuum. Okay, so we got the circuit, we got the function. That's the important thing. We could apply the circuit function, the quantum node, to input and output, and we get the results straight away. Okay, and because the data it's no longer a tensor at this point, it's become an array. We can run it the second time, and we can see that we get it's actually I'm just plotting the outcome here. So we have the same values, and the plot histogram is also in my library. Now, if we want, we could actually look at every single gradient attached to the weights. And the weights actually are not attached to specific values. They get the gradients get changed during the circuit run. That circuit was running 1,000 times. Okay, 1,000 times. And so the gradients were changing every time the circuit was running. So how is it working? Where the gradients are? Okay, so the gradients are here we have 3 qubits, we have 4 weights, and it ran 1,000 times. And so where the gradients are. So basically the gradients is actually giving us a matrix. It gives you the probability of measuring the specific state on the kth weight. And it's a Jacobian matrix. So those of you who are physicists, you know exactly what I'm talking about. And Jacobian matrices are common in data science as well. And at the moment, I'm just telling you, yep, the gradients are complicated things. So if we actually produce the gradients, watch here, are producing the gradients, I specify the function. There is a function which will be running the circuit, taking input and output 1,000 times, and watching as the gradients are changing. And only then it will produce the Jacobian matrix, which is sort of like the average gradient. Okay. Okay, this circuit, let's run it twice. And each time it gives you slightly different results, which is expected because it's a probability distribution. Each time we run, we have the quantum effect at the measurement. And so we expect some variation. Okay, is it possible to create the whole big table of data and run it through the circuit? Well, let's create it. Let's create a stack of the same input, and pass it in. So this is the data that I've created. And if you were running it on Qiskit using something like a regressor and the estimator, then it will suck it in and produce results, in this case, for 5 times, 4 possible outcomes, because there's 2 qubits here. Okay, so 2 qubits, so 4 possible outcomes. Okay, what happens here? That's a bizarre. Why don't we get 5 outcomes for each data item we plugged it in? Well, this is not what this circuit is doing. This circuit takes inputs. If the input is one vector of 2 values, that's what it does. It attaches one value to input 0, one value to input 1. The weights get distributed and produces the outcome, one at a time. What happens when I put here the whole lot of values? It's an array of this kind. Well, that's what it takes. It takes the 0 item and puts it to the first variable, input variable. It takes, sorry, this is not, this is the gradient, sorry. So it takes the 0 element and attaches it to the first input variable. It takes the first variable, attaches to the second variable, and then you have, obviously, 2 different outcomes. How is it possible that we attach to multiple values to that variable? Now, what Pendelane does, it uses so-called broadcasting. So you could actually attach a stack of values to a single parameter, and to each parameter, as long as they have the same values. That circuit will be created and then applied multiple times very efficiently to every single value coming to different input variables. So it works differently than Qiskit. So how do we write a circuit which is able to consume a table of values? We need to be very specific. We just remember that the entire table, the entire array, the tensor, is going to be passed in as input. So this is a version of the same circuit which takes batched inputs. So it's very similar, except that now, instead of taking the zero item, I know it's a table there, I take a slice through this table and say the zero item of every single row gets stacked onto this variable, onto this parameter. And here we have another slice. We take the first value of every single vector coming on the second parameter. Everything else the same. The weights are not stacked, so it will use the same weights every time. So now, when we execute it, it's the same circuit. It looks the same. Nothing changed. It's just that during execution, we get now 5 outcomes because those 5 values each will have been stacked on the parameters. So if you get confused at this point, don't worry. You could always just plug one value at a time and do it in a loop. But this is much more efficient because we rely on the fact that the circuit may have been loaded into your NVIDIA card, and the data will be joined and executed in one go. Okay, so it's about efficiency. We could measure the same circuit differently. Just looking at my time. So it's exactly like the first circuit, except that now I'm going to return 2 measurements. They are expected values of measurement onto z-axis. So this is actually specifying how we're going to do projective measurement. So it's amplitude against the z-axis. And since we have 2 qubits, so this will be run twice and will create 2 measurements, one attached to qubit 0, one attached to qubit 1. It will still look the same, but there are different types of measurements. So before, those measurements together, they produce probability distribution. This time, they will simply give expectation values from the state of every qubit. So what do we expect on the result? Well, we expect for a single input, very simple data or a vector of 2 values, which get encoded on input. We expect 2 values on output. Okay, so those are the expectation values. Note that they could be negative because expectation values are from -1 to 1. So there's the histogram of this. And of course, the gradients will be appropriately different. So no longer we have very complex structural gradients because the measurements are simpler. Now, what if we have a batch of values? So if we have this more complicated input, this is exactly the same structure as before for the batched version of the circuit, except now I return different measurement results. And instantly I'm going to run it on multiple input with weights. And that could be also unexpected because before we were getting nice tabular data. However, before we had a single observable. So that's one observable special. It's a probability distribution. It's a one outcome is being returned. So that one outcome was accumulated and presented to you. Here, I specifically say that I want to get two outcomes, a list of measurements of qubit 1, 0 and qubit 1. And I ask for that, that's what I'm getting. So basically, if I stacked the values onto um, the rotation gate with 0 and then from 1, the vectors, the slices, I get as many results as the measurements were taken. So if I want to get it in a nice way that I expect it to get, I need to transpose it. Okay, so that's actually useful if you want to work in batches. If you have a file of 10,000 values, that will never happen because you can't broadcast such a big vector in penny lanes. But if you work in batches, like normally would do with deep learning, so you could stack, let's say, 150 values, that's well accommodated, and that circuit will be running very, very efficiently in one go on an accelerator. Okay, any questions? There's a lot of questions here. Again, if you get confused about that, it's not a problem because you could be running in a loop, going through a table of inputs, putting them into your circuit, getting results one at a time, accumulating them. But this is a much more efficient way of doing it. If we go to the challenge question, we're going to rely on that. Okay, so that's the first walkthrough. And if you did it beforehand, I'm not sure if you understood it because penny lane very poorly explains this at all. And quite often when you run penny lane circuits, you could get weird error messages, such as this tape, there's multiple tapes running. What is a tape? A tape is your circuit, abstract representation in terms of the sequence of operations, quantum operations. So a tape is moving the state of the circuit from one gate to another, okay, until measurement. So that's a tape. A tape is sort of like an abstract representation of a circuit. And you could be getting some unexpected results, like here. I wanted to have 100 outcomes and I got only 2. Why? Because that's what you did. You asked to have the first value from the input, the big table, the second value from the big table, and you put it to the operation. So only 2 outcomes will be, only 2 values will be put in, and whatever probability will be based on this. Okay, so sometimes this will be confusing. All right, so let's move to the next example. This example, a real example, I'm going to construct a very simple function, the function sine that you should be familiar with. So this notebook, and here I'll bring it back. It has a number of tasks. Okay, so I'm going to walk you through the tasks. Let me restart the kernel and clear all the results. This first statement is to make sure that the tables are adjusted to the left. Let's go into action. In this notebook, unlike other notebooks, I'm going to show you where in the code are actions I want you to perform. And the tasks on the right-hand side, I say task 1, task 2, task 3. And it says, yep, in this task, do the following things, just to make your life easier. And then as we move into the second session, the third session, I'm going to forget about doing this because you'll be experts on finding where to change things. Okay, so I attached PennyLane and importantly, the NumPy as NP from PennyLane library. I'm going to create a sine function, and then I'm going to create a circuit of 2 qubits. It'll have a number of layers, and I'm going to train it on 20 epochs. And I also provide some random seed, which I'm going to pass to different random processes. So we have the same results every time. So data preparation, it's very simple. Note I have two data sets here. One, if I want to use another one, I'm going to uncomment this one, comment this one, and we'll switch. So it's a sine function from -6 to 6. Okay, that should ring the bell. Or -6 to 6. I specify device, the same as before, the number of qubits. Yep, number of qubits will be the number of wires. And shots is none. What does it mean, the shots is none? Don't we want to run it 1,000 times? Because we're using default qubit, this is basically the device which uses statistical distribution of results. So it knows upfront what should be the distribution of results when you run it. Okay, so that's convenient. The inconvenient thing is that it will not happen like this on a real device, but we can see next presentations, and it will be happening fast. I'm creating a very simple model. I have three models here, model 1, model 2, model 3. So this model is a single rotation gate around the y-axis by input value x. It has some weights, which are parameters. That's attached to wire 0, which is the qubit. And I'm using entanglement layer. You're going to see that in a minute. So basically, it's a template from Penlane, standard template of parameterized parameters with correlation, with entanglements, and they return expectation values on one qubit, 0. Again, it's a projective measurement on axis Z. I have two others, which I'm going to discuss later. Because they all have the same structure, I simply say, I'm going to use model 1, and the code will be identical underneath. So that is referring, yep, no, model 1 will be used, the first one. Now, what happens is that we're going to rely on gradients and use the gradient-based optimizer. So it means that optimizer has to understand every algorithm which is used in the process because the gradients are propagating through the code. And so my cost function needs to be written in a very simple way because the propagation of weights and other aspects and the results, it needs to be visible to the optimizer. So instead of using mean square error from another library, like scikit-learn, I write my own. Once we get into Torch, the Torch replaces all this complexity, and we could rely on PyTorch libraries and cost estimations. Okay, so this is basically comparing targets to predictions in a loop, very boring and very inefficient, and gives you mean square error. And there's another function, cost function, which takes parameters, inputs and targets, and then basically for all the inputs on the list, we'll run the model called QNN model, which that model takes the weights, that model takes the input and creates the circuit. And that circuit executes and creates the predictions. So we have a list of predictions. So basically that function is actually a shortcut of taking a long set of inputs. So I'm not using broadcasting. I'm simply feeding one at a time. Remember I mentioned if you get confused in the previous one, we could run it in a loop. That's what we do here. So I have here inputs. I have a very simple model. And one item at a time, I'm running the model and producing results in the list. And then I take the list of predictions compared to targets. I get a list, I get mean square error calculated that way. Okay, so now we have two different ways of entangling and creating the blocks. I just, there's helper functions which return the shape. I'll talk about it in a second. In Pendelane, it's very important that the weights have shapes. So if you have structures, which I'm going to show you in a second, here I'm going to create the model. I create some parameters because I will not be able to see the model unless I actually feed some data to it. I got some results, and I can actually print it. This is the ugly way of doing it, Pendelane. But if you want to send your model via email, that's easy, text email. And this is to use MPL version of it, which is matplotlib version. And you can see it's a lot of statements here. You can use my version, which is in my utilities. Okay, so this is the model we created. And that's why we needed to have some test parameters. Otherwise, we wouldn't be able to see this. Okay, so this is the model. The model is a function. Keep it in mind. The model is in function. So now I'm going to select my optimizer. I use the Pendelane optimizer, Adam optimizer, some step, large. I initialize now the real parameters for my task. And the training loop is simple. So those of you who already you train deep learning models, this is very simple. You understand this. So I'm going to collect costs in a list. So I'm going to run it, run the model one step at a time, apply to different data. And as optimize is running, it will be one step at a time. So here's the loop, the iteration loop. And the optimizer is running one step and calculate the cost. And I'm using here my cost function. This is the dummy function, which will take parameters, and one parameter at a time from whatever it was delivered will be put into cost function and returns the new parameters and the calculated cost. The cost is appended to the list and until finished. So the training is happening here. If you are used to TensorFlow, you're probably surprised everything here is so ugly because everything is explicit. Okay, we actually do it ourselves. So this is the plot of what we've done. And those are the predictions. So already we get a good result, except that it looks like the model is not doing much. It's just saying, and the next value is like what I have. So it looks pretty dumb. This is the echoing effect, and we never trust the model which does that. Okay, so we had a good result. How could we get such a good result? Okay, we have a number of challenge tasks, and let's look at the next task to do. The next task is, can we improve it some way? For example, we could improve it by changing the model initialization values. At the moment, initialization values, the weights, initial weights are very large. Normally with models, by the machine learning models, like neural networks, we want to keep the values non-zero but small. So it may improve. So let's try to do that. Somewhere here, I'm having actually, I create the model and then I initialize it. So where is it happening? Yeah. Okay. So this is the highest value is pi. Let's multiply by 0.2. I'm going to run everything from top to bottom and observe the result and see if there's any difference. Okay. So some smaller values did appear. So it looks like there was some effect. Using smaller weights has a good effect. It can see it flattens out and I get better values. It's still doing the echoes. Even though clearly I was getting a smaller mean square error. Okay, there are some questions. What is echoing effect? The echoing effect is the model which predicts things in sequence. It says, my current value is 5. I predict that in the future it's going to be 5. And it's a good prediction if it's a time series and it's absolutely nonsense prediction. It just assumes that the world is never changing, but your error is small. You know what I see? So this is a bad predictive model. It's the echoing model, which doesn't do any work. It just says the next value coming in the future will be the value which is current. That's the echo effect. Okay. It may have a different name as well. Okay, so what else can we do? Let's give it more time. Maybe it could be given more time. So at the very top, I specify epochs 20. Let's make it 50. Would it work? Is it going to be an improvement? Well, we get some smaller values straight away for some reason. And yeah, we get actually improvement here above 20. Clearly, it's a good outcome. Okay, so I propose to do some more experiments, like changing the actual structure of the circuit. Let's try to do this. So the structure of the circuit is here, and we could specify, for example, that instead of using, at the moment, the circuit looks like this. So it uses only a single rotation on around y-axis. How about if we use rotations around y, x, y, and z? Okay, so this means we're going to use a different entangling approach. I'm going to use strongly entangled circuit, which actually relies on 3 trainable parameters per operation. But that will require a bit of thinking, because suddenly I have 2 different circuits. You can see that the shape of my weights is different. Okay, let's print the circuit if we can. But for that, I need to actually create my parameters differently. So now you can see the shape of parameters is here. Before it was 2-dimensional parameters because there was one rotation. So we had 4 layers on 2 qubits. 4 qubits, 2 layers, 1 parameter each. Now we have 4 qubits, 2 layers, 3 parameters, x, y, and z rotation. And so if I use what I had before, I would get, oh, I didn't get an error because I haven't used it yet. The model is now using a different input. This is the ugly way. I can comment it out so that it doesn't interfere with us. And this is the structure. If I try to initialize it as before, I would still get probably that outcome, but it would fail later on. Okay, so now again, I need to use different shape initialization. The weights in pendulane are not flat. The weights follow the structure. So the weight structure is the structure of the circuit. So when we actually try to initialize it, it's a bit like in PyTorch. We have here 2 qubits. We have how many layers? 1, 2, 3, 4 layers. And then each parameter is 3 values. X, Y, and Z. Sorry. All RZ, RY, RZ. Okay, so it's equivalent to the rotations around three axes. Okay, so now we can run the optimizer. And the training should be happening. Now we have more parameters to deal with, and hopefully we get a better result. Hopefully. It's much slower because the simulator is working much harder. It's many more parameters than before. But I can see that we start getting really good results in there. Okay, so we had to work very hard. Okay, I have here the ridiculous question. Can the model work with a single qubit and single layer? Hopefully, would it produce any result? I wonder. Would it work? Well, here we had to train it so hard. We had to add more parameters to improve the result. What if we had a very ridiculous approach? Okay, so let's make it ridiculous. I'm going to make one qubit, one layer. Let's make 10 epochs. It should clearly fail, right? Will it fail? I have three parameters. I could make it even simpler. So we're getting some result. Okay, and if I actually made a single parameter instead of three, I'll get a better result. Why is that so? Any ideas? Why? In fact, if I remove all parameters and leave only a rotation rotation gate, I'll get a perfect result. Why could that be? Okay, no ideas? The thing is that if we had a model, well, the function is simple, but it's better than that. Okay. The function is a single rotation. If I remove all those three gates, I'll get a better result. This is rotation around the qubit. If we generate that rotation around the qubit, we get a sine function. A single gate will actually generate this result. Okay, so it just happened that our data is a sine function. A single rotation gate will actually provide the sine function if we manipulate it, rotate it. So if we give it x, different values of x, and we rotate it around the Bloch sphere, the result will be the sine or cosine with some shift that it may learn. Okay, so this is the issue here is the data is such that of course we could train it and learn it, but the data is actually mimicking what rotation gates are doing. So it's unfair. So let's use a different data set and see what we can do. So in this case, I'm going to go back to what we had, 4 qubits. Number of layers were 2, make it more, 4. 100 epochs, and use more difficult data set. So I'm going to use a slightly different looking data set. Let's restart the kernel and run it all above. That looks like the same data, yeah? It's a sine data, but shifted in phase from -6 to 6. Okay, and we're going to leave it strongly entangled. So the model will be more complex. So let's go to what it looks like. You can see it's a very sophisticated model. Now that model has one This is a single rotation which encodes the data. Everything else are parameters, trainable parameters that are going to learn this, which we learned with a single gate in single qubit a moment ago. So let's run it and see what we get. Okay, so at the moment it's a bit on waiting time. The model is complex. I'm running it on my relatively large machine. It's a gaming computer with lots of memory. I have a big GPU, but I don't use it for this exercise. So if you're looking to get involved in quantum machine learning, I suggest forget your laptop, get some floor top machine with a lot of memory and with a lot of power and a big CPU and maybe a big GPU. So that's actually very useful if you want to save money on developing online. In the past, I used to go to various services online and build my own machine and pay like $50 a month or $100 a month. Okay, so I decided to spend a few dollars on my own computer, and this way I could do most of my experiments at home. And in fact, my computer is faster than a lot of computers you could build online for money. Okay, so what's happening here? It looks like our model is not learning anything. Why is that so? It's bizarre situation. You can see before we had 0, 0, 0, 5, and now we have 3, 1, 1, 1, 1, 1, 1. That is not fair. I made the model so complex. It should be learning something, but it's not learning anything. Um, that's what it looks like. It looks like it converged, but this is the result. Now, what I'm suggesting here, experiment with that until good. But um, what I can tell you right now, it doesn't matter what you do to this model. It doesn't matter if you use a different model. Um, a lot of people who try the simple sign function, there's some online places in Penny Lane, and people are conversing. They just change a little bit, they shift the sign function, and suddenly the model stops learning. And when they get this result, people's advice is, your model is not expressive enough. Okay, give more qubits, more layers, more parameters, and you're not going to fix that problem. Number of shots. Okay, you could use 1,000 shots. Okay. It will not fix it. Okay. Um, okay. Any ideas I can give you right now, tell you you will not be able to fix it. Why won't you be able to fix it, whereas before on the sine function it works so beautiful? Any ideas? Okay, the answer to this is here. Okay, so mapping the values from in the range of -6 to 6, exactly as it is here. So the representation of values are wrapping around from 0 to pi. Then we have overlap, the amplitude already matching amplitude of what was encoded from 0 to pi. It then wraps around further um, to 6. So, sorry, it's up to here. And it's -6, so the opposite way. There's a lot of conflicting values in this representation. So the problem is not the model. The problem is encoding. What we need to do is to shrink the range of encoded values somehow and then replicate it and see if that works. So that's a good lesson. If we follow through all possible changes, nothing is going to fix the problem. The problem will be fixed by changing our encoding strategy, which is where the data was created. Okay, I'm going to add a single statement here. So after data was generated, I'm going to say, yep, my x coordinates will be x shrinking by 4. Now I'm going to make it much simpler. Number of qubits 2, number of layers 4, make it 50 as it was. Let's run it and see if that will fix it. All I did was changing the encoding because encoding strategy created conflicts in my states of in the representation of data right at the very beginning. So it's training. You can see it's already learning something. 0.4. So clearly we have a better outcome. And if we give it more complexity and more time, it will give you a better fit. Okay, it didn't learn much. So let's actually try to use different model. We need to have a break. So I'm going to just specify that I want to model 3 and just run it once before you go and enjoy your time having coffee. I'm using the re-uploading model. Let's observe the loop, which means that I repeat the encoded value across not only in a single qubit, but across all qubits, and then across all layers. And re-uploading of data, it fantastically improves training of the model. Just that the reminder of the optimizer. Here's my data again inside my representation. And that's almost a perfect outcome. Okay. So just to show you the model, which we did, you can see we have here RY, RY. So this is the encoded value X, which is the same value encoded on qubit 0 and qubit 1. And then again, after the layer of parameters, the same value and the same value, and so on. Just reminding the system, this is the value I'm encoding. This is the value which is input. And that actually really changed what was the result. So we did a model which fixed things. The problem here was not the complexity of the model. To some extent, yes, because we improved it with re-uploading layers. But the problem was we made bad choices in the way we were encoding data in the circuit. Someone asked, where was the change? The change was here. So I shrunk the range of values from -6 to +6 to smaller range from 1.5, whatever it is, to -1.5 to 1.5. So that shrinking that range, it reduces the conflicting of representation.
Okay, Mateusz, I can see that you have raised your hand, so I believe you would like to ask a question, right?
If you have
Yes,
questions, go ahead.
yes, I would like to. So we talked about the compression of our data in the between 0 and pi, right? To kind of express the angle. All the data inside of the 180-degree angle, let's say in
Yeah.
real values, right?
Yep.
So is there a so we talked about the data that overlaps itself when this problem arises, like from -6 to 6, it overlaps. But is there another side of the problem? So if I have too much data to compress into this tiny space so that I lose the game of, let's say, resolution.
True. True.
Is that also the case?
It is the case.
And when it happens, if you could explain it, it would be nice.
Okay, so basically, angle encoding is fine as long as you don't have too much data to encode. So you need to have a good resolution between different representations of your data in terms of your amplitude eventually. And so one thing to compensate would be to have, if you use it on a normal quantum machine or simulator, is to have more shots. The more shots you have, the more precision you're going to get. Here we use the simulator, which relies on statistical distribution, so it gives you precise outcome. However, the problem, as you said, if we have a lot of data a lot of possible data values to be packed into small space, then we have a problem. One issue is never try to put so much data into a single qubit. So that's why we have multiple qubits. And so if you use, for example, the amplitude encoding, that it distributes possible values across not only multiple qubits, but you have also representation in terms of layers. So you have more scope for encoding data. There's a lot of encoding approaches to deal with. First of all, to deal with the conflict of encoding data. Secondly, to increase the precision. Okay, so that's the fact of life. Yes, we don't have here at the moment. We don't have the quantum machines that the quantum noise is going to kill you anyway. So if the quantum noise is, let's say, 2% on fidelity is 99.98. That's nowhere near the precision you get on a classical machine. Okay, so that noise on a quantum machine is going to upset all your precision. So precision at the moment is not there. Because then the difference between consecutive values on your Bloch sphere will be eliminated with noise on the measurement. Make sense?
Yeah, absolutely, yes.
So yeah, so we need to be clear about that. So we need to use multiple qubits for the representation. We need to be able to use sort of distributed representations across the whole circuit. And that's why re-uploading data is so significant, so that that precision is not lost throughout the computation. But here, the problem was basically the conflicting encoding, so that by shrinking the range of values to be encoded, we eliminated the problem that multiple different values would map into the same position on a Bloch sphere to start with. So there is no difference at the coding stage between different values to be processed.
Okay, can I expand on this?
Yeah.
So if we have, let's say, I see that I have not, let's say, 50 points or something like that, but I have 2000. So
Yeah.
now I think that, okay, it's too much. I would like to use another qubit, let's say, to encode the angle.
Well,
So
I think that,
what I wanted to say is that if when I use two angles or even three angles, if I decide to three, so now my problem becomes like three-dimensional. Is that correct?
true.
Because
Yeah.
I use three angles and I can pack my all data in 3 dimensions.
Yeah.
Right? Okay,
Sure.
okay.
And your problem is easily getting into multi-dimensional space. So, but that's the beauty of the quantum approach, is that you could solve your problems in in a high-dimensional quantum space where it could resolve a lot of issues, eliminate. We have some interference here. Okay. All right, we're going slowly back um, to the presentation. We have still 1 minute. Yeah. Yeah. So the thing is that by shifting the whole idea would be to use the representation of data, and then shift most of the problem processing into Hilbert space. That's ideally where the solution should happen. However, we don't have now as yet the algorithms which could optimize the models in Hilbert space very effectively. So if you're a physicist and you're modeling some physical processes, electronic interactions, and you could very precisely create a Hamiltonian of the process and look for looking for ground state. Okay, and virtually it's a very precise operation. If you look at business applications, you don't have any precision, and it's very difficult. So we rely on classical methods more until we learn how to do it properly in a quantum space.
Okay, so if I could yet another question, another question. I'm sorry, this would be the last one, I promise.
Yeah, no problem.
So if I encode in 3 angles, or rather I encode when I use 3 qubits, I encode it in 3 angles, or rather I encode it in 6 angles because I have like 0 and 1 outputs. That my qubit could collapse. So now those two are perpendicular to each other. So I am in kind of maybe in the terms of tensor product, I am in 8-dimensional space, right?
Yep.
So I encode in 8-dimensional space, or I choose 3 angles and I encode like that, or I do something completely different.
Okay. If you have very complex data, what I would do is to use a trainable feature map. So here we have a very complex data, a lot of data. I wouldn't try to encode it directly. I would try to create the feature map, which could be trained on your data for the best representation. So that's done in kernel methods, for example. So it's a quantum kernel methods. All the effort goes into creating the feature map. And then you could use even classical method on that. So with very complex data, the effort goes into finding the best representation for your data. And then the second problem is to solve the problem with this data. Make sense?
Okay, yeah.
Okay. So rather than trying to
Thank you.
figure out how to use 3 qubits X, Y, Z rotations to increase your representation power, I would be using maybe a kernel, quantum kernel to learn the best representation for your data. That would be my solution. Okay,
Makes
I
sense.
hope
Thank you.
everybody, I hope everybody's slowly getting back. And this is the second session. According to official plan, it's the third session, but we collapsed the first 2 sessions into one. First of all, let me just reflect on what we did so far, because I'm pretty sure that a lot of people got swamped off their feet and you think this was tough or too much, too fast. Okay, so first, I introduced some basic concepts, and probably nobody had serious problems with that, with the actual slide presentation. The problems may have started when I gave you my tiny model, which the aim was to give you some idea what the circuit looks like, how the circuit is created. The circuit is a function. The circuit takes inputs and weights as parameters. And the circuit is built as a side effect of running the circuit, which means unlike in other toolkits, quantum toolkits, which you stitch the circuit statically in front of you, You have a circuit, you could investigate it, you could look at the connections, you could print it. In penny lane, that's not how it happens. The penny lane circuit is created as the function runs. Okay, so that's very much like what happening in photonic systems, where the state of the circuit is stitched up as the laser is manipulating the state of the circuit and entangling it, and the circuit goes into vacuum. Okay, so the circuit is not static. The circuit is created as a side effect of running the function. I also showed you how to pass individual input values to it. And to give you understanding, there's no magic happening. Your function actually gives you exactly the method of using the data. If you pass individual data item, that's what it does. If you give it a table of data, you need to be clever to extract the data and rely on parameter broadcasting. It's a separate story. Okay, so if you got lost in that, you can always do one item at a time and collect it. Okay, but there's a better way of doing more efficient. What you should also know is that the vital part to penny lane quantum machine learning are gradients. The gradients are attached to weights. The gradients are complex multidimensional features, and that was to show you that on the Jacobian matrix, the gradients are in multidimensional space, and the gradient, if you do 1,000 runs, we have 1,000 versions of those gradients that need to be somehow presented in a meaningful way. Okay, so the other thing we talked about was actually different ways of measuring outcomes using probabilistic measurements and using exponential expectation values. The values which are projective measurements, so we have poly-Z operators, projective measurements against some axis. We normally, when we talk about in introductory classes, we think, yep, measurement is against Z axis. But if you talked about physics and chemistry, the observable are very complex structures, and they're not necessarily against your orthogonal axis. So there should be ability to create very complex observables, measurements of your outcome. We stay with simple ones. We have expectation values, which we'll rely on quite often. They don't exist directly in Qiskit, for example. In Qiskit, if you want to get expectation value returned as a measurement, you need to do a bit of create an estimator and calculate it. Okay, so it's different. Everything's different in penny lane. And why is it different? Penny lane created structures and facilities where the gradients could be propagated through the model and the calculation in a very efficient way. That's why everything is a function. That's why the gradients require cost functions to be differentiable. Any function must be differentiable, or else it will not work directly. Okay, so then I showed you that model here, simple model using sine and how to train it. And then we discovered that because we are using data, which is basically mirroring the behavior of a qubit operation, I was getting good result accidentally, even though my data was incorrectly encoded. And because the function was symmetric and the conflicting codes accidentally happened to overlap precisely, it is a sine function, I was getting good results straight away, even with a single qubit. But if I shifted that function a little bit slightly, everything collapsed. Everything collapsed not because the model wasn't complex enough, not because we were not clever, or not because we didn't give it enough time to wait. We could not actually train that model at all because we badly encoded data. We created conflicts at the very beginning, so the model could not distinguish between different data values. They would be mapping onto the same code in the circuit. So the problem was to change the encoding, and then suddenly we were getting good results. And they could be improved. So it's in your homework, it will be good for you to walk through those two notebooks and try to figure it out. There's a lot of tasks that you could follow and try to play with it and see what's the result. Actually, one good exercise here, somewhere here, I said, change the data encoding gate from RY to RX, and then everything stops working. And then you answer yourself, why? Why stops working? Okay, so there's a lot of thinking points in those tasks that you may want to go through and do it and observe the effects. Okay, so we know what was the problem, but try to do it without skipping the points and activities. Okay, so we are now into session 2, and in this session, I'm going to talk about quantum estimators. So let me get the slide. In this session, I'm going to do a bit of mix and match. I'm going to talk about the principles of machine learning and principles of quantum machine learning, and you're going to get the best of two worlds. Okay, and that's what's happening every session. All right, so we're going to look at quantum estimators. That means we want to estimate a value. We don't do classification. We don't want to classify data into 2 or 3 groups. We want to be able to predict a value. Okay, so could be predict the age of the person, predict amount to be paid, predict the temperature in the room. Okay, first, let me just forget about all the predictive stuff. Let's talk a little bit about the whole process of quantum model development. And what you see here is not necessarily quantum stuff at all. It's a process of software development. It's a process of machine learning development. It's a development process which relies on data. So first, normally in a normal business situation, you need to state a business problem, which is grounded in the business needs and the requirements. Okay, so that's what we're starting with. So we don't start with developing a model or collecting data. We need to know what is the problem we're trying to solve. That's number one. Then we start collecting data to figure out how to represent the data, how to select what data is most representative of the population, to understand the data, to look at so-called priors, different weights and probabilities in data and statistical profile of the data. So that's exploration, preparation, repairing data, and so on. You're very familiar with that if you come from machine learning and the data science background, analytics. The really difficult thing is to find and discover relationships in the data, and some data types are very difficult to do so. For example, if you look at let's say a temporal data, the time series of signals. The data seems to be very uniform and flat, but there is a lot of features hidden in the data. Or if you look at social media activities, there's a lot of interconnections between people and the conversations, and the relationships are dynamic and hidden, that they come and are born and die. Okay, then it's time to develop and apply some analytic model, which could be quantum model. And the model needs to be constructed, applied to data, then evaluated, improved. And normally it's not happening in isolation, as I'm not aware of a single quantum application which is not embedded in a larger computational structure. So definitely it needs to fit into the way you acquire data, then you integrate the results into some kind of a visualization, and someone has to make a decision based on this. So that's this integration in a larger scale of things. And then if it's any good, you deploy it and manage analytic solutions in a business environment. It could be engineering or scientific environment. Someone's going to look at the charts and make decisions. Then at some point you assess results, and could be that you need to go back and redefine problems, and business problems require more data, understand it, develop models, and the loop closes. Somewhere in that circle, there is space for research and innovation and reflection. And in quantum area, that's consumes a lot of energy, is to do research in this space. Everything at the moment is basically research. Although the hardware people, they are much better at this because the hardware is far, far ahead of the software at the moment. Okay, so we're getting closer to what we're trying to do. Normally, if you talk about modeling, we have some classical modeling and quantum modeling, and there's some relationship between them. So if you look about estimation models, we want to predict some continuous numerical value or target. That's in contrast to classification models where we predict discrete labels. So what type of models have those estimation capabilities? They're linear regression models, whether it's ordinary least square regression or Ridge or lasso regression. It's nonlinear regression models, polynomial, support vector regression, Bayesian modeling, probabilistic models, and then neural networks, which seem to be at the moment, I think neural network, it's like a silver bullet. It fixes all problems. And there's a variety of them. So convolutional neural networks, recurrent neural networks, and so on. There's a lot of time series forecasting models, and then you could put ensembles of those models into big buckets of different models working together. Now, when it comes to a quantum estimation model, we don't have such range of available tools. So what happens there is the models are useful in some situations. So we can't actually simply do it, create a quantum model because we have a quantum machine and access to it. There must be good reason where we use quantum modeling. So those reasons could be that we deal with high dimensional data already, so you could map it onto one-to-one to high dimensional quantum space. We could have some noisy environments, noises in the environment, noise in the data, or very highly complex calculations. So number 3 is currently occupying people's minds, especially in high energy physics, where complex calculations are difficult and time-consuming on the classical machine. The applications are many, and one mentioned physics. So energy area and physics and chemistry are the prime targets for quantum computing at the moment, and then of course networking and security. But then you have finance, like risk assessment, stock price prediction, in healthcare, drug effectiveness, demand forecasting, inventory optimization in retail, and so on. So all of them are to do with predicting some continuous values. So quantum models capable of doing that. Just the staple diet of quantum machine learning is quantum neural networks, of course, and quantum kernel methods. Okay, so that replaces shifting data into high dimensional space. We just shift it into Hilbert space and operate in there. Okay, so we have data now. And this is boring stuff for people coming from machine learning. How do we create the model? How do we test the model? How do we know the model works? How do you know the model is going to work in the future? So, so those of you who come from non-computer science background, it may be useful to you. Of course, if you have a data, you collected data, and you train the model on this data, and at some point, the model stops learning. So that's basically you use the same data for building the model and testing the model. All you know is whether the model still has capacity to learn, but you don't know how effective is that model for new data? Can it generalize that learning to new data? So that is fine. It has limitations because we cannot generalize, we cannot make any educated guesses about its applicability to data it had never seen. So what we normally do, we can split the data into 3 parts. And this is called the holdout testing approach. It splits the large part of data for training, so the data could be used for the optimizer to test and then improve the parameters and so on. Then you would validate the data, so it's a test. You get results, you find out what's wrong, you go back to training, and then the circle, it oscillates to training, validation, until we get the model which works well on the validation data and training data. The question is, will it work on the data it had never seen before? So we left one partition, data partition, for that purpose. It's so-called honest testing. We apply the model to that partition to see what happens if we apply the data it had never seen before. It never been used in any part of the model development. Okay. Now, when we work with quantum models, we may have a bit of a problem because it could take many hours to train the model and validate. You oscillate that, and then you need to test it independently. You may not even have data for that. Okay, so it's a question, do you need to have 3 partitions, only 2? But this is not the best way of doing it because we could have been lucky the way we split the data in training and validation. So one way is to solve it, is to have a cycle of random sampling of data for training, validation, and testing, and then repeat it many times and take average. So that's one way. Another way is to use cross-validation technique, where we split your data into a number of parts, of folds, and let's say 10. We train the model on 9, then validate it on the 1 which was left out from training, and then we repeat it for every single fold to train on 9 and validate on 1, and then get the average. So that's very commonly done, cross-validation. That's what we normally do in normal machine learning. But what about quantum stuff? Again, if your model is trained not in seconds, but in days, that's a lot of work. You could spread the testing and then development across many machines, many threads of your single machine, and it's still expensive, especially if you need to pay for that. So that's not commonly done in quantum machine learning, but this is required for many applications. So if you want to get good faith in the performance of the model, this is what's needed. What's the additional problem? The additional problem that you've seen in the last session is that the quantum models are very sensitive to the initialization of weights. So if you start 10 runs and each is differently the same model, the same data, the same split and partition, but the only thing is difference in initialization, you may have vastly different results. So ideally, every run that you have should be maybe replicated 10 times with different initial values, and only then you would look at the statistical performance measures. So it means we don't have 10 runs, we have 100 runs. So it's getting very, very expensive. So you need to be clever about that. Most of the people use perhaps the holdout testing with random selection of partitions and repeat it a few times. But cross-validation, ideal, but may not be very realistic in quantum machine learning. How is training happening in quantum, well, in Pendelane in particular? What? We have 10 o'clock, okay. So first of all, everything in Pendelane is a function, okay? So the circuit is a function. That's a bit unusual. And the way we normally organize the creation of the circuit, we create a function which actually spins out the circuit factory. The circuit factory, which creates a rich environment of other variables, which would be available to the circuit function. Normally, the circuit function takes only two arguments, your input and the weights. But you may want to know other things. You may want to know about other data. So you need to be able to create a rich environment, sort of like a class. So you create instances of the class with additional information which the instance has access to. But we can do it in a functional way, purely functional way, because everything in penny lane needs to be differentiable. So ideally, the functions should be creating functions. What else we need? Apart of the circuit, we need to be able to have weight parameters and input parameters. The weight parameters need to have gradients. The circuit itself is responsible for evolving the state from the initial state to the final state. And we need to have some measurements. So those aspects need to be built into your circuit. And the creating factory of circuits need to understand it. It needs to understand what is the architecture of the circuit and what are the meta parameters in terms of how many qubits, how many layers of what kind, and so on. Okay, that's pretty much what we understand already from common sense and machine learning. Now, the circuit is what's closest to the Hilbert space, because when it's executing the evolution of the state, that's happening in Hilbert space. But all the optimization of the circuit is happening in the classical space. Okay, so we need to have an optimizer. We've seen it, Adam, Nadam, others. There will be a training loop. The training loop, which will feed the optimizer with initial weights. The optimizer at each step is going to calculate the cost using X and Y coordinates of the data, will calculate the cost and the new weights for the next step of the optimization. The training loop needs to be able to create some log of the performance, and maybe the parameters should be saved as well. So this is a typical scenario for creation of the circuit and optimization of the circuit. And I mentioned here the optimizer will need those gradients that will allow it to navigate the cost landscape in search for the lowest cost, which is the bottom of the valley, global bottom of the valley. So we got the quantum, we want to be able to track the quantum model performance. And definitely what we need is to have, once the model gets trained, we only get the training performance. But the models get overtrained and could be very quickly overtrained. So what we need is to be able to collect the model parameters as they were evolving during the optimization. And then once the training finished, we need to be able to create a mirror image of that model, exactly the same architecture, and load it with those parameters and apply it to data, the testing data or validation data. Okay, so we could calculate mean square error for each model applied to the test data. We could compare your training and testing performance. In this case, beautiful, they converge. But we want to maybe have other type of performance indicators. So this is called scoring of the model. We use the model and its parameters and apply it to same data and calculate different performance measures like R squared, the coefficient of determination, which could be useful for regression style of modeling. Maybe many others, mean absolute error and so on. Okay, so definitely we need to have model training, then find the testing indicators, performance indicators, then score it on using other performance indicators. That's fine. We get those charts. Is that enough? No, we need to be able to understand where the model is making mistakes. Okay, so it's in relation to data. So what we might to do is to look at the errors produced and different spectrum of values, where the expected values, which is your training from the training data. So here is a chart. It's a residual as a percentage of values. So before training, the errors were ranging from minus 20% of values up to 100% of values. And so we have a testing and training data errors. We can see the spread of errors. That's a nice chart, but it's not very meaningful. We can only see that after training, the errors reduced to about 20% and maybe 10% in negative value. That's fine. That is beautiful, but not helpful. There are better ways of doing. So we need to the diagnostics of errors in a simple way. For example, we could plot predicted values versus expected values. The truth is that line. So it's the predicted value and expected value should be the same, but the predictions could be oscillating. So if you look at expected value versus predicted value, it oscillates and perhaps it's magnifying in some points. So when the predicted value is high, the error is largest. Okay, so that's good, but we need to see what happens in aggregate form. So what we can do is to have a residual histogram where we accumulate the errors produced in certain ranges of residual value. So what it gives us, if you were to put your model into work, let's say into a production of cars, and so the model makes mistakes, and then you have to pay with dollars from your pocket for every mistake it makes. So that actually tells you what is the aggregate costs in certain range of residual values. Okay, so it's not where the errors are small. Not where the errors are large, but where the errors are small. So this is small error made, but there's a lot of errors happening this way. So the residual cost is high in training, it's reduced in testing, and the residual error, the total error cost is elsewhere. So you could actually analyze where it's worth to put the effort to reduce your errors. So perhaps it's not where the cost is high because it happens not very often, but where the cost is low. And thinking that way is risky. So you need to look at some risk factors there. You may remember the explosion of some oil rig near the US state, because nobody worried about rare events which are high cost until it happened. And it was a huge disaster with billions of dollars. So you need to look at both the high cost, but rare events. So we need to be able to do some diagnostic charts and try to figure out where the errors are happening and then try to figure out why. So we need to have some understanding, locate where the errors happen, understand why the errors are happening, then eliminate them. That is nothing quantum. That's just plain machine learning. Now, a good question often is, the model stop learning. Is it stop learning because of what? Does it have capacity to learn? And there are some special techniques which are actually applicable specifically to quantum models. So there's some concept of effective dimension, global effective and local effective dimension, which give us an idea that whether the model is still able to learn. So we learn, we train it, and is it still have capacity to learn? How much? And so there are some statistical methods to determine that, and it's especially good with avoiding so-called barren plateaus, the flat areas of cost where the model is searching for solution, cannot find it. So it's not that the model is not learning because it has no more capacity, it's just got stuck in a barren plateau where the learning is hard. You cannot find the optimum. So this is just one of my past projects, which you could find in this publications, the impact of barren plateaus on neural network capacity to learn, where we looked at different methods of eliminating the problem with barren plateaus, and we specifically look at the model's capacity to learn. So sometimes the model has huge capacity to learn, but it cannot do so because it's stuck in a barren plateau. And sometimes the process of eliminating barren plateaus, it causes that the model is losing capacity to learn because which we interfere with the model structure. Okay, so there are some specific techniques. In fact, in Qiskit, there is a function which calculates effective dimension directly. Now, in all the quantum machine learning, people forget that that we actually have classical models which do the same. And we say, yep, we've got the quantum model. And some people say, okay, let's compare it to classical model. And we pick up a neural network off the shelf, we run it against it, and quantum model performs fantastically, and the classical model is terrible. And why is that so? Because people spend months and months tuning the quantum model, and they take the model, classical model, off the shelf, and nobody bothers actually do anything to improve it. And this is a typical what I found in many papers. People don't spend time trying to optimize the classical model equivalent to a quantum model. So they need to be honest and spend at least as much time tuning your classical model as you tune the quantum model. That's another project here, which I did with Sebastian, who is the mentor. And we were actually comparing different quantum models in different circumstances, and then comparing to the classical model. We actually found that we could beat by a very tiny fraction of performance of a classical model, but we didn't give it sufficient time to learn. We fixed the number of epochs of training on classical and quantum models. But yep, if someone says, I've got the quantum model which beats classical model, show it to me and prove it to me. And as long as you spend as much time tuning the classical model as you spend the quantum model. Okay. So this is actually hard. Now, this is a well-known phenomenon, the curse of dimensionality. And what is it? I mentioned barren plateaus. So let's say you have a model which cannot find the optimum. We know the optimum exists somewhere in the landscape of the cost function, but because that landscape is very flat, your optimizer is looking around, browsing around, looking for the hole to go down for to find the optimum cost and then the best model. So the barren plateaus, it's the reason why it's happening is actually, it's not that it exists, it emerges, and it exists because your model has very large number of dimensions, especially in the parameter space, because that's where it affects the optimizer. Why does it happen? Okay, so it's nothing to do with machine learning or quantum machine learning. It's to do with the high dimensional spaces. Imagine we have a ball. Okay, so we have two-dimensional ball is a circle. Three-dimensional ball is a sphere. Four-dimensional ball, it may be harder to imagine, but it's a four-dimensional ball. And then you have high-dimensional, 45-dimensional ball. If you look at the mathematics of calculating the volume and the surface of multidimensional balls, the mathematics is well known. So it's an interesting phenomenon. If you look at the volume of a low-dimensional ball, the volume of the low-dimensional ball is high compared to its radius and the surface. Now, once the dimensions go higher and higher, what you find is that the volume of that high-dimensional ball concentrates close to the surface, and the space available, the volume is shrinking with high dimensions. So if in this high-dimensional space, the parameter space, if you distribute your model, optimized models as points, if it's a low-dimensional ball, so space is low-dimensional, and imagine that the cost is the lowest cost in the middle, and the high cost is outside. So the landscape, the cost landscape here has enough space to have valleys and hills that the optimizer could navigate and find the descending line towards the bottom. When we actually have a lot of parameters, the area available for the cost landscape is becoming limited and it flattens. So the optimizer, especially when it starts navigating from the point far away from the optimum, has virtually no hope of finding the descending line towards the optimum, the bottom of that pit. So this is nothing to do with machine learning. It's nothing to do with quantum stuff. This is to do with the mathematics of high-dimensional spaces. Okay. You could actually also find interesting things that if you look at pairwise distances between points in that high-dimensional balls, you find that the distances between them are shrinking. So they all become very close to the mean. So the distances between all points become very close, even though you would think intuition says high-dimensional ball is a lot of space. Yeah, the high-dimensional ball, the space is shrinking in it, and everything is getting flat. So that's what's called barren plateau in quantum machine learning. It's just that the cost landscape is getting flatter and flatter. It's more difficult for the optimizer to find the optimum. And so what can we do about it? There's a lot of known ways of dealing with that. You could use fewer qubits, fewer layers, fewer parameters. Yeah, tell me that. I need to solve my problem. I need to represent the problem. The circuit has to be expressive enough to be able to represent the problem we're solving. But that's no solution. Use local cost function. Do not measure all qubits. That's nothing to do with that problem. It's to do with the sparsity of your measurements that populate that space. Okay, but that's a different problem to do with high dimensionality. You could use non-Euclidean metrics. So if you use the normal metric, everything is flat. If you could use some exponential metric which blows up the dimensions, then you could compensate for the shrinking space. Try not to use random parameter initialization because you could end up too far from the optimum. So if you work on chemistry problems, for example, which are very high-dimensional problems, what people do is to first look at the classical method to get the required parameters as close to the optimum as possible, and only then use the quantum methods. So once you're close to the optimum, you could find the way down. Use barren plateau resistant model design. So you could train the model layer by layer until all layers exhausted. That will get you to the point close to the optimum, and then you could retrain the model from that point on. It could use also barren plateau resistant models like convolutional neural networks, where the filter moving around, that's the picture, is low dimensional. And so it reduces dimensionality of the problem, full stop. Okay, so we have some barriers to quantum estimation. We have lots of solutions, which you are listed here. I'm running out of time, so I'll get into demo. So I'm going to show you the model where we're going to estimate data. And it's a very artificial synthetic data set, but it's fun to work with. And then there's a problem for you can do for homework. You're going to look at the data, which is more complex and very colorful. Okay, so we're going to deal here with a simple estimator. We're going to create a quantum regression model. So what is the data? Okay, the data is picked from an external source. And where I get it from, I can find out. Okay, I can't remember where I got it from, but I use here, oops, that's what happens when you don't have enough memory. Why don't I have? Sorry, let me just restart everything. Okay, so I'm using data from, I think it's a scikit-learn data set. Okay, so scikit-learn. So what is the data? That looks like a lot of points in three-dimensional space, but if you rotate it, you can see there is actually a plane in three-dimensional space with some random noise injected. Okay, so definitely, if you had to determine if the point belongs to the space or not, it's a regression problem. It's just in three-dimensional space. So the first thing is to set some parameters, and the most important will be the parameters for encoding the data. So I know that I need to encode the data in some area from 0 to pi, maybe, not maybe from going over to pi. And I will also give some margins in case during the rotations of the qubit state, I'm going to flip on the other side. So I'm going to shrink that available space of the rotations. So I'm going to make encode the data in as the angle from 0 to pi, leaving some margins around. The model will have 2 wires, 5 layers to start with. And I'm going to parameterize that problem so that I don't need to worry about whether I'm using what type of entanglement I'm going to use. I'm going to build it into my modeling. So I'm going to use initially basic entanglement and some information for the optimizers, how many epochs, how many shots, and how often I want to print results of the optimization. So the first thing I'm going to do, I've got the data here, and I have X and Y coordinates. And the X and Y coordinates, X is actually having 2 dimensions, I think. Oh, target. So it's a X, Y, and its target is up. I think that's how it works here. So I'm splitting the data into part for training and part for testing, and making all partitions to be tensors. Okay, so that's the first thing here. I insist on making them tensors. They are penny lane NumPy, so they are tensors, and they don't require gradients because they're not weights. They are just plain data. The cost function, the loss function is similar as before. It's just that I slightly redefined the cost function. So the cost function, remember the last time, it knew what type of model I'm using. So it actually referred to the model directly. But what I'm going to do here, I'm going to create the cost function factory. And that cost function factory will actually produce the cost function as a result, which means that the cost function itself will know via its generator what model it's using. Okay, it will. So basically, this cost function will be returned as a result. The function generating cost function will know what model it will be applicable to and what cost function I'm going to use, this one. And so this variable within this cost function will be available as a non-local variable. So it will preserve its environment of the function generating it. So those people who never use it, that's actually, you'll find this is commonly used in penny lane because everything is a function, everything must be a function. You'll see that in action in a second. So I'm going to create the simulators, the same default qubit and device. So I'm using default qubit device. And this is another function which creates function. Okay, so I will create a model which is the linear regression model, but it is really, when you think about it, it is a neural network. Okay, it's a neural network. It consists of angle encoding block and entangling block. So what's going to happen is that the function which creates that model, a function, the parent, the generator, it will know how many qubits, how many layers, whether to scale the weights or not, and what type of entangling block we want to use. This will be created by the generating function and referred to as non-local variables within the function which is returned as a result, the actual model. And inside, I'm going to create an angle encoding block, and depending on this variable, I will create either the basic entangling layers, just one rotation around the y-axis, or strongly entangling layers, where the rotation is around x, y, and actually it's actually z, y, z, but it gives you around all three axes. And it's going to return the expectation value on 1 qubit. Okay, let's see how it works. Now, before, remember, you said, I was saying, every time I try to change the entangling basic to strongly, I had to worry about it, where I need to change it inside the code. I'm going to actually create a shape function. I mentioned before that in PenLane, like in PyTorch, the weights are not flat. In Qiskit, when you deal with a model and you create the weights, there is a perception the weights is just a flat vector. But inside, they're attached to different operations. So in PenLane, as in PyTorch, the weight structure is not flat. Why is not flat? It actually tells you what are the layers of weights within the model. Why do you need that? That's actually good for the optimizer, which wants to apply backpropagation inside the layer by layer. So it actually knows which layers are close to the measurement, which layers are away from the measurement. And if you run it on a simulator, you could actually run a backpropagation algorithm on weights layer by layer backwards. So that's actually very convenient. Okay, so you need to know what is the structure of weights inside the model. And there is a helper function which tells you this is the shape of basic entangling layer, and this is the shape of strongly entangling layer. So now I'm creating the quantum linear model. Okay, first of all, I'm calling the factory function, the factory function which specify how many layers, how many wires, and what type of entanglement I want to use, so basic entanglement. And I will not use a decorator this time. I will so this is a function. This model is a function. It's a function returned by the factory function. So now I could actually pass this function to the Q node. So I could explicitly create the quantum node and specify the device on which this quantum node is going to execute. This is the circuit function. Now I could specify what is the shape of its weights by knowing the number of wires, number of layers, and what type of entangling I'm going to get. And how do I know it? Because I wrote the function to tell me that. So this way, I'm just structuring my logic so that it's more manageable to play with. So now I can create my parameters just for testing. It's a random uniform distribution in this shape. So if it's got it's a complex structure, it will tell you how complex it is. And because they're weights, it requires gradients. So now I can actually see it. As you can see, it's a lot of work, but I've got the same that we used before. Okay, so except that now I have actually two different values on input, and then we have layers and layers of weights and a single measurement. Okay, so now I know it's got 10 weights, and I can train it over 50 epochs. And the training is the same as before. So I have some random initialization so that it's replicable. I'm going to use Atom Optimizer. Step size is huge. We could improve it. I now get the cost function again from the cost function generator, which is the factory function, which will pass the model. So this cost function will actually know what model it is applying to data. And it will also know what is the loss function that I need to use. So this is the cost function. That's a function which is actually the result of running the function which will create it. Those of you who haven't seen this before, this looks like there must be some mistake, yeah? Okay, so this is now all the same as before. I run it in a loop, optimization step, except that now I not only collect the cost, but also collect the parameters of the model. So it's happening. It will be slower probably on your laptop. And what we need now is scoring. Okay, so I'll get the cost for the training, but I don't have the cost for tests. And so I have here the calculation of now what I did this, which this is what that's required to do. No, okay. So here I'm applying, I calculate another score, which is R squared for training data only. So this time I'm going to get the model and I'm going to use the parameters which are saved before. Okay, so I'll load the model with the parameters and then I could apply that model to and use different scoring function. And this time I use the standard scoring function because I'm not training the model. It doesn't have to be, the function does not have to be nice and smooth and with all the weights. So I calculate R squared for training data. Okay, it happened very quickly. So I calculated now with my mean square error for train and R squared for training data. I don't have those scores for the validation or test data. And that is your homework, which is very simple. You know the structure, how we do it. Actually, here I have all the logic, which I did it, but you don't have it in your code. So we can plot it and look at the performance. It's nice and smooth. So this is training and testing performance using mean square error. And here is training and testing performance using R squared. Okay, so I get the results. We can also calculate the errors, the residuals. And again, it's your exercise for homework. And you could plot it as a scatter plot. And you could plot it also, this is actually, I included that for you to have a look. And variety of, once you calculate the residuals, which is the errors, you could plot it in many different ways as a histogram or truth versus prediction, which here is terrible. But your job will be to make it better. Okay, so this is actually, we still have half an hour, yes. Sorry, 20, I'm just looking at the time. Yep, we have time. So we can actually play with it a little bit. I'm just looking at time. Yeah. Okay. So here there's a lot of challenges for you to do, and I show you the bare bones. So what's difficult here? The first difficult concept is that concept of a factory function. Those of you who know the how to work with classes and instances in object-oriented way in Python, this is not much different. So basically, you could consider this as a class which creates local. You could have local variables, and those local variables become non-local inside the function which is declared inside it. So when this function is returned and runs, it actually has access to the context, the environment of the function which created it at the time of creation. Okay, so this is very much like class and instance situation, but this is purely functional. So there's no side effects here, which means that the models are differentiable. And this is the main idea of doing this trick rather than using classes and instances. So that's important for penny lane because penny lane is all about differential programming and using gradients propagating through functions that we construct. The next thing we learned is that there are some standard templates, which we used before. The angle embedding, which creates the positional angles for each qubit, and they simply roll them out and create them across the circuit. Okay, so all we need to do is to specify how many, so we need to specify how many inputs we have and over how many wires, and it will simply create all the gates for you. Okay. The entangling blocks, the same way. There's a standard template for rotation on a single rotation or triple rotations. Okay, so we have a simple rotation, and if we change that, if we specify that we want to use basic false, is going to be more complex structure. And we could do it. We could try to run it because we still have time. So for example, how can we improve this? Can we improve that? And here I have some steps for you to do. So we're walking through step one. Can we improve the selected model by changing entangling method from basic to complex to strongly? All we have to do in this structure is to change the parameter value to false. If I step through this again, remember they need to be tensors. So always remember to don't pass arrays only. Luckily, in penny lane, the numpy in penny lane, automatically we create the tensors. But this is a very explicit way of stating the same fact. This numpy is a tensor already, okay? But this is a very explicit way of saying it's a tensor and whether it's good gradients or not. The cost function with the cost function generator, again, the same trick. The cost function will require 3 parameters when it's used, but we actually create an environment where it's got more knowledge. It will know what model I'm going to use. It doesn't have to rely on global model that is being referred to as before. So I'm just showing you how to better modularize this whole thing, how to ensure that every single component is a function and that function is differentiable. Okay, so this is now, we should be able to get more complex data structure. You can see now every operation has the 3 arguments. So we have 3 times as many parameters in this circuit. It will be much slower to execute. Okay, so we're going to train it. Is training happening? Oh, here we go. Whether or not it's going to be an improvement is going to be interesting. I think that the last score will be better. We perhaps need to give it more time for training. Yep. So it's actually we got a lower score already, and it's improving further. So indeed, we get the benefit. What would be good is to get the three-dimensional representation of it. The data is actually in 3 dimensions. So whether or not we could actually do it. I'm scoring it. So at the moment, all I do is to looking at performance plots, which only tell us, yeah, with this structure, with more parameters, perhaps we would get benefit of giving it more epochs because it's still pointing down. It's still pointing up when it comes to coefficient of determination. And perhaps before we had residual chart, we showed 100%, up to 100% of errors. Maybe, yet we reduced it to 50% of errors. And here the chart maybe is going to be lower, indeed. And those charts are interesting. You can see how much error we had against the truth. And now we get quite an improvement. So we can see we can actually work on the model. It's a lot of sweat, it's a lot of time, and it's a lot of persistence. And you would say, yep, this job is not for me. But then if you're in machine learning, then it's exciting. If you're in quantum stuff, you think, yeah, I'm learning new stuff about how to do it properly, how to improve, how to measure improvement. The fact that we need to ask the question, is the model generalizable to data it had never seen before? So we need to have tests. We could assess the effectiveness of the testing using a variety of different scores. We learn how to apply, once we created the optimal model, in training, that may not be the best model for testing. It may be overtrained. So we need to actually apply to test data and retrace all of the applications of intermediate models that the optimizer found and apply to test data at each point to find at which point the model performed best for data it never seen before. So what is to be done for you? Okay, so I hope you're sitting in front of this notebook and you ponder what to do with your life. You may want to try to fiddle with it and see how it works. The hardest part will be here for you is to probably understand those factory functions. But as you notice, I think that as we get more sophisticated in it and we start encapsulating penny complexity into functions, suddenly it looks very much similar to what you may have done using other tools. So we shift the complexity now from creating the models into the creation of the training loops and optimization and playing with a lot of classical components that you may be familiar with from your other world, the other experience. If you come from physics, then maybe this is the most valuable part because maybe in physics they never taught you those aspects. If you come from computer science, then I hope you struggled a little bit with quantum nodes. Another thing that was new here is the way we were creating models before we used the decorators, the QNode decorator. And here we explicitly create the quantum node programmatically. There's no more magic. Now we can see the whole creation of a circuit is done in phases. So in our case, we use the quantum model generator to create a function which actually creates the model. This is an abstract function. It's just plain Python. the Python which will call, it make calls to penny lane APIs, but it's just Python. To be able to make it executable on a quantum device, we are explicitly making a quantum node, which this creates a wrapper around your function, which will prepare the quantum node. And then every time we call to creation of the gate, it will collect this gate and attach it to what it calls the tape. And the tape is a sequence of operations which need to be executed once it exits the function creating the model. It holds the tape, and then this tape is compiled for this device when the circuit, or this is the tape, is executed. So the execution of quantum linear model, it needs to take weights of a specific shape. And this is important because the structure of this model is not flat. So Qiskit actually has a lot of problems with that because the Qiskit is a black box of parameters. And so they used clever methods to determine what is the structure of the circuit. Okay, whereas here, the shape of the weights, it determines which layer is closer to the measurement and which layer is further and which layer is closer to encoding section. Okay, so this is important. Remember that weights have shapes. The weights need to have gradients. The gradients are needed for the optimizer. That's a gradient-based optimizer, Adam optimizer. Okay, so that's a bit of complexity, but I think that by now you can see there's a logic in this. We started with, perhaps it was chaotic, but we started with basic things, how you pass parameters into the circuit. Everything is a function. Okay, are there any questions? Okay, I have how applicable circuit cutting technique in quantum ML algorithm from practical point of view. I don't know what you're talking about. Circuit cutting, you're talking about structuring it. Yeah, it's important when you have a lot of qubits and you may need to restructure it. Okay, the homework. We have homework for session one. Session one had homework, make it better for, but you know, I gave you all secrets out, but play with it because the session one homework, it reveals the complexity, okay? This session, there's a lot of missing bits here, and the bits missing are, you can see, there's actually full data reuploading model. There's a reuploading model in session one. I show you how to construct the layers of data in between the layers. Here we can actually restructure this code to, as we create layers, we need to be able to inject angle embedding in it. The problem with this call is that it actually injected strongly entangling layer, which is multiple layer structure. So you may need to actually do it by hand, the way we did it in session one. Okay, so that's a bit of a rethinking. This is very convenient because it creates a multi-layer structure. But if you want to every layer inject angle embedding, we need to do it in stages. We can't simply call it repeatedly because it will create operations, the parameters with the same name. So we need to be clever about that. You need to actually look at what are the parameters of this, or do it by hand in a loop, injecting angle embedding, or create your own code for adding parameters and coding the data. So you will create a custom model to do angle reuploading model. So there's a lot of here, the instructions, just follow the instructions. And there's also another data set here. So if you still have time in your life, there's a data set which looks like, where is the data set? I think it's here. Okay, so this is actually the Swiss roll data set. Okay, so it's a similar problem, how you fit the data into this layer and whether the data is in this layer or not. So it's a regression problem, but regression not around the line, not about around the plane in 3 dimensions. We try to fit the data into a multidimensional structure, okay? And the color is representing the amplitude on the structure. So the color is your y dimension. Okay, so you can play with that if you have time. Otherwise, there's a lot of work to do here to do the classical things, you know, how to create those charts, how to do the scoring using different measurement, which you could get. For scoring, you can use scikit-learn operations. You only need to have differentiable scoring functions during the training. That's where the gradients need to pass through the code. Okay, so we have here other solutions to the task questions. No. Okay. I have solutions, yes, but I'm not giving them. That's because we hope you're going to step through it and do it, and there will be a quiz which asks about things you're going to learn from doing it. Okay. Is there any quiz? The quiz is after the whole workshop. And so within a week, so I think that the minute workshop finishes, the quiz will be distributed and you'll be advised on Discord. And you'll have a week to do the quiz. It's not complicated. I can't remember how many questions, but there's maybe 30 questions in the quiz. And the quiz is going to 27 questions. And it's a very simple quiz. So if you listen, you understand. I think understanding is the key. And we really want you to, the thing is what you've learned today, it was a lot of learning. Okay, so if you think you're lost, I can understand this. You still have time before tomorrow. It's a Saturday. What a waste of Saturday. But you have time to actually try to figure out what you've learned today. It will get reinforced tomorrow because we're going to do, tomorrow we're going to work on classification. And then the last session is going to look at how to create hybrid models using PyTorch and Penylane. And the last session is about creating quantum autoencoders. And again, the task will be to convert the Penylane autoencoder into a hybrid PyTorch Penylane autoencoder. So we start from very simple things in the morning today. You thought it was very difficult, of course. And we progressively make it more difficult. So sort of from 0 to hero in 2 days. And the last topic will be advanced. But by that time, hopefully you will really get it. So it's important that you try to revise what we covered. And you try to actually run it. You dirty your hands, you look at it, you stare at it, you can see slow improvements. You browse through the code to understand it. Okay, so we are still having some time. So if you have any questions, is the homework the same as the challenge? No, I actually say here often, what is the challenge? The challenge tasks. Perform the following task in your own time. Complete unfinished task. Change the model by incorporating re-uploading ansatz. I didn't show it to you at all. It's not here. So re-uploading ansatz for this task is much harder than, you have example of re-uploading ansatz in session 1. The code was given, okay, which we actually run as the very last minute. I just say, use re-uploading ansatz, but I never spend time investigating it. Okay. And then, use Swiss roll. I said use either real estate valuation or Swiss roll. I did not include real estate valuation here. So Swiss roll is another data set, which is another regression task. If you get lost, you could look at Swiss roll data set and you will find some more explanation of what it is and how to work with that. So browse around. Don't try to rely too much on AI agents. The deadline is you may need to have some of this knowledge. We will not test if you've done the challenge. We hope you've done it because it could help you with the quiz. I will not ask specific questions about, there'll be no questions in the quiz specifically on the challenge using Swiss roll. But when you do it, the work you do is important, okay? If you don't get to the challenge, don't worry, because you can still pass the quiz doing the compulsory tasks. The recording. The recording will be available at some stage.
Yes,
Yep.
Jacob. So this meeting is recorded, so everything depends on how long we'll process it. So usually Zoom processes the recordings in a few hours, but the question is if we would like to introduce any changes to the recording. So basically, it's up to you, Jacob.
Yeah. I think in the past we used to cut out the coffee break.
Yes,
Yeah. So that
we can do. Yeah, but yeah, I think it can take a few days.
Mhm.
Uh, but I think it's still okay, right? So people should still have a few days to do the quizzes.
Is quiz to be objective? Um, it's a multiple choice quiz.
Yes. There's a question from Mateusz, I think, or at least his hand is raised.
Where's the question?
Mateusz?
Yes, so could you go back for a slight moment to the slides where you presented um, the multidimensional ball and its problem with the embedding in 45 dimensions or something like that.
Okay. Yep. Okay.
And you then there was like a slide in further, like 2 slides further, where you or 2 slides back, where you explained something like a fitting. Oh yeah, that one. No,
Okay.
this one. Oh God.
Is that the one?
No. Uh, 2 slides further.
This?
Yes. Yeah. One more. I will tell you. I will tell you. I'm sorry. Oh yes, this one. This one. Yes.
Okay.
Global effective dimension. Global
Okay.
effective dimension. So
This
what
one?
global effective dimension?
Yep.
Yes, okay. Because there is a refresh delay probably in my on my side
Okay.
compared to yours.
Okay.
So I didn't see it at time. Anyway, uh how does it relate to the barren plateaus in terms of if the because we see that on the side, right? So on the y-axis, you have the local effective dimension, and there is a number of data. So is
Okay.
the local effective dimension when it is lower, does it help barren plateaus, or when is it higher, does it
Okay. So when
bad?
it's higher, it has more capacity to learn. When it's
Okay,
when it's lower, it's a low capacity to learn. So in a sense, uh, when it's higher, it's actually actively has more capacity to learn at any point in time. So local effective dimension is a dynamic measurement, and it also gives you capacity to learn per parameter. Okay, so it is actually slightly confusing because it says basically how much capacity a single parameter in a model has for further learning. So if your model has a lot of parameters, sometimes it gets dissolved and it looks like it has less capacity to learn because um, it's per parameter. And if you have few parameters, so you need it's a balance. So that was actually here somewhere. I had 4 different models that we were looking to counteract barren plateaus. So we were investigating whether the methods of dealing with barren plateaus are actually reducing capacity to learn. Okay, so it was actually interesting because we're not actually looking for barren plateaus here. We didn't actually diagnose whether the model is facing barren plateaus, but we applied the specific techniques for avoiding barren plateaus or reducing barren plateaus. And we're observing whether that action of dealing with barren plateaus in the model is actually having impact on its ability to learn. And we found that some methods were actually, they were dealing with barren plateaus, but reducing the model's ability to learn. Okay, so it was it's basically like we are applying the good method to make it worse. That was the conclusion. So some methods, the best method was the layer-wise learning, where you train the model layer by layer, and which means you deal with very few parameters at each point. And when you get to the end of training, so definitely there's no barren plateaus because each stage is using very few parameters. So we never get to high dimensional space. So when you finish, your model is not accurate yet. It's not optimum, but it's close to the optimum. So we could then use the weights it learned in the process as the initialization for the new learning stage. So we are close to the optimum and then finds the optimum quickly.
So it's not even like using right optimizer or something like that. It's like the entire method of training.
Yeah. So it is.
Okay.
So it's a structure of the model, and it is also the way we. So, for example, there's another one which you train the model in blocks, and the blocks have mirror image of each other. So it's retraining. So there's a paper on that. You could get it on from quantum information processing, which we wrote. So there's another effective method was do nothing. I think method 0 was do nothing, which actually said, yeah, that method was brilliant. And we use random initializations, basically against all advice of everybody. And the method was, in our experiments, was beating all other methods, except that we know that this is not an effective method because the model wasn't complex enough to suffer from high dimensionality. So, so basically, yes, we need to figure out if you face barren plateaus, and then this method works. But if you do face barren plateaus, it's been already determined that this is a bad approach. Okay, so that was an interesting series of experiments, and we used the global effective dimension is interesting. It measures the model capacity for learning before we train it. So it looks basically at the geometry of the model in high dimensional space, and it gives you some estimate how much learning it is capable of doing. And the local effective dimension at each step of the optimization, you calculate its effective dimension, and then you determine whether at the end of training the model still has capacity to learn or not. Okay.
How do you calculate this effective dimension? Is it like some well-known functions, for example, I don't know,
Yeah,
information
that
gain or
paper
something
has
like that?
all details. So if you want
Okay.
to, I can send you the paper as well. So if you
Okay. Okay.
send me email, or send it um, on Discord, and I'll send you the paper.
Okay. Thank you.
Okay. Okay. Any other questions? We still have 2 minutes to go. So, what I hope messages there. We have week after tutorial finishes. Okay, so I think Pavel was answering all those questions. Okay, I don't know if there's any. If you had any question that wasn't answered before, please do it now. Otherwise, yes. Otherwise, we'll see. I'll see you all tomorrow. And thank you for attending. And I don't know. We still have 85 people, which is great. We started with about 116. Some people had to go home. Okay, so thank you so much. And good luck thinking about it. If you get stuck, remember that on Discord, we are monitoring your questions. I'm in Australia, so between now and the next hours, I'll be asleep. But we have our mentors who could answer your questions. So thank you and see you tomorrow.
Thank you. Thank you, Jacob. Thank you, Jacob, for a great session. And thanks everyone for attending. I'll see you tomorrow. I will now stop recording.
Thanks, Pavel.